On September 5th, 1977, at 12:56 Coordinated Universal Time, a Titan 3E Centaur rocket lifted away from Launch Complex 41 at Cape Canaveral. As the engines burned and the lower stages separated, Voyager 1 was released onto a trajectory that would carry it away from Earth, away from the planets, and eventually away from the Sun itself. At the time, the launch did not look like the beginning of something endless. It looked like the start of a mission with clear limits. A sequence of planetary encounters, a stream of data, a spacecraft expected to do its work and then fall silent. Nothing about Voyager 1 was designed with the assumption that it would still be operating decades later. Nearly 50 years later, the most remarkable fact is not how far Voyager 1 has gone, but that it is still functioning at all. The spacecraft released that day is still moving through space. It is still powered, it is still measuring its surroundings, and it is still sending information back to Earth, even though the signals now take many hours to arrive and reach their destination, as whispers pulled from background noise. That persistence is not dramatic. There is no visible struggle. Voyager continues because the same physical laws that carried it away from Earth continue to apply. Momentum carries it forward. Energy drains away at a steady, predictable rate. Systems shut down one by one as power becomes scarce. What remains keeps working because nothing has yet forced it to stop. Space does not rush things, it wears them down quietly. Since launch, Voyager has endured environments that could never be fully anticipated. Temperatures have fallen toward absolute zero. Radiation has accumulated slowly, particle by particle, year after year. Its power source has weakened not through malfunction, but through the natural decay of its fuel, following a curve that was known in advance and impossible to change. Each year leaves less margin than the one before, and still Voyager responds. Commands sent from Earth continue to reach it, though they arrive long after they are transmitted. Responses return later still, describing conditions that existed hours earlier. Voyager is always reporting from the past. Its present cannot be observed directly, only reconstructed once the signal completes its long journey home. That ongoing exchange was never guaranteed. It exists only because the spacecraft survived long enough for it to continue. As Voyager moved outward, it passed beyond familiar planetary space into regions that had never been directly measured before. The influence of the Sun weakened gradually. Particle densities thinned. Magnetic fields shifted in subtle ways. There was no sharp boundary, no visible edge, only slow transitions detectable through careful measurement over long periods of time. These are changes that cannot be captured quickly. They reveal themselves only through patience. Short missions glimpse places, long missions reveal structure. Voyager did not simply travel far, it travelled long enough for space itself to change around it. What makes the mission unusual is not that it succeeded, but that it outlasted its original purpose. The planned encounters ended decades ago. Voyager completed its primary task and then continued onward, transforming from a planetary probe into something rarer, a continuous experiment in endurance. It does not adapt, it does not learn, it does not decide to continue. It persists because its systems still function, and because space offers almost nothing to slow it down. Once set in motion, the universe does not interfere unless something substantial stands in the way. This story is not about a destination. There is no arrival waiting ahead. There is only continued motion through an environment that grows thinner, quieter, and more uniform with every passing year. The question is no longer what Voyager was meant to do. The question is what it has shown simply by continuing to exist. What space looks like when observed slowly. How distance accumulates when nothing interrupts it. How time stretches when measured not in events but in uninterrupted motion. Voyager continues to move steadily away from its point of origin. As long as it does, the journey remains unfinished. Welcome to the Sleepy Scientist. If this is the kind of calm, curious space you enjoy drifting through, consider giving the video a like and subscribing to the channel. It quietly helps these stories reach the people who might need them most. And before settling in, take a moment to leave a comment and say where you're watching from. A city, a country, or just a corner of the world wrapped in night. It's always fascinating to see how far these sleepy ideas travel. The story begins on Earth, long before Voyager ever left it, in a moment when space exploration still felt new enough to be shaped by optimism rather than habit. The 1970s were a transitional decade for science and engineering. Computers were shrinking in size but growing in capability. Radio communication had matured to the point where signals could be sent reliably across millions, then billions of kilometers. Rockets had become dependable enough that failure was no longer assumed, but exploration was still expensive enough that every mission had to justify itself carefully. This was not an era of casual experimentation. Every component had to earn its place. Every gram of mass had to be argued for. Deep space probes were not yet routine. Sending a machine past the outer planets was considered ambitious, risky, and potentially wasteful if it failed. Yet at the same time, a quiet confidence had begun to take hold. Humans had already reached the moon. Robotic spacecraft had flown past Mars, Venus, and Jupiter. The solar system no longer felt unreachable, it felt incomplete. A major part of that confidence came from advances in electronics. Solid-state components had begun to replace older, more fragile systems. Circuits became smaller, more reliable, and less sensitive to vibration. Memory was limited but predictable. Engineers could now design machines that would behave consistently for years, even decades, without physical maintenance. That reliability mattered more than raw power. A deep space probe could not be fixed. It had to work the first time, and then keep working. Radio communication advanced in parallel. Large dish antennas on Earth, combined with increasingly precise tracking techniques, made it possible to communicate with spacecraft far beyond the orbit of Mars. The Deep Space Network, operated by NASA, expanded into a global system of listening posts spaced around the planet. As Earth rotated, at least one antenna would always be pointed toward the spacecraft. This infrastructure made long-distance exploration practical rather than theoretical. Rocket technology also reached a turning point. The Saturn rockets that carried humans to the moon proved that heavy payloads could be delivered reliably. Smaller but powerful launch vehicles could now place probes onto complex trajectories with extraordinary precision. Escaping Earth was no longer the challenge. Choosing where to go after that became the real problem. Within this context, scientists and engineers began to think differently about the outer planets. Jupiter, Saturn, Uranus, and Neptune were not just distant lights in the sky. They were physical worlds with atmospheres, magnetic fields, and moons. They were laboratories for understanding gravity, chemistry, and planetary formation on a scale Earth could never offer. One organization in particular became central to turning those ideas into reality. The Jet Propulsion Laboratory, managed by the California Institute of Technology for NASA, had already built a reputation for robotic exploration. It specialized in missions that required long durations, autonomous systems, and careful navigation. Rather than treating spacecraft as short-lived experiments, the laboratory began thinking in terms of endurance. Around this time, astronomers identified something rare and temporary. The outer planets were approaching a configuration that would not repeat for well over a century. Jupiter, Saturn, Uranus, and Neptune were arranged in such a way that a single spacecraft could visit them in sequence, using each planet's gravity to gain speed and redirect its path. This was not a coincidence of convenience. It was an opportunity dictated by orbital mechanics. Planets move at different speeds around the Sun. Their alignments change slowly and predictably. Occasionally, those paths line up just right. When they do, gravity itself can be used as a tool. The principle behind this is simple to describe, even if difficult to execute. A spacecraft approaching a planet falls into its gravitational field. As it swings past, the planet's motion adds energy to the spacecraft's trajectory. The spacecraft leaves moving faster and in a new direction, without burning additional fuel. In essence, momentum is borrowed from the planet. The amount borrowed is small compared to the planet's mass, but transformative for the spacecraft. This technique, known as gravity assist, had been demonstrated before, but never on such an ambitious scale. By chaining these encounters together, a probe could reach distances that would otherwise require impossible amounts of fuel. The discovery of this alignment transformed what had been a vague idea into a concrete plan. Early mission proposals were cautious: fly past Jupiter, perhaps Saturn, return images and measurements. That alone would have been considered a success. Anything beyond that was uncertain. Hardware limitations, power constraints, and unknown environmental hazards made long-term survival unlikely. Yet optimism crept in, not as blind hope, but as calculated confidence. Engineers realized that if the spacecraft survived longer than expected, it could simply keep going. There was no requirement to stop it, no reason to turn it around. Space does not impose borders. Once a machine escapes the Sun's immediate grasp, it can continue outward indefinitely. This shifted the philosophy of the mission. Voyager was no longer designed only as a planetary visitor. It became, quietly, an experiment in persistence. It was built with redundancy, with backup systems, and with the ability to operate autonomously if Earth fell silent. It was given just enough intelligence to protect itself, but not enough to change its purpose. The cultural backdrop mattered too. The Cold War still shaped global politics, but space exploration had begun to soften into something less confrontational. Voyager carried no weapons, no flags planted on foreign soil. It was openly scientific. Its data would be shared. Its discoveries would belong to anyone who cared to understand them. That openness reflected a broader shift in scientific culture. Knowledge was becoming collaborative. Planetary science drew from physics, chemistry, geology, and astronomy at once. Understanding Jupiter's storms required fluid dynamics. Understanding Saturn's rings required gravitational modelling. Voyager was built to serve many disciplines, not just one. There was also a sense of humility embedded in the mission. No one pretended to know what would be found. Instruments were designed to measure broadly, to observe rather than confirm. The mission plan allowed for surprise, which is not something engineering projects always tolerate. When Voyager left Earth, it carried the assumptions, limitations, and aspirations of its time. It reflected a belief that careful design could compensate for uncertainty, that patience could substitute for speed. That understanding might come not from dramatic moments, but from steady accumulation. Leaving Earth behind was not just a physical act. It was a conceptual one. The spacecraft represented a decision to look outward without expecting an immediate return, to invest decades in answers that might arrive slowly or only partially, to trust that future scientists, many not yet born, would still be listening. That decision shaped everything that followed. The science, the engineering, the way the mission would be remembered. Voyager did not begin as a symbol. It began as a tool, a carefully constructed machine launched at a particular moment in history, carrying with it the quiet confidence that if it was built well enough, it could outlast its own expectations. Designing Voyager was an exercise in admitting ignorance without letting it become paralysis. The engineers and scientists involved understood a simple truth from the beginning. Once the spacecraft left Earth, it would be on its own. There would be no repairs, no upgrades, and no second chances. Whatever it encountered beyond the planets would have to be faced with the tools it carried from launch day. That reality shaped every design decision. The first challenge was structural. Launch is violent. Even a successful launch subjects a spacecraft to intense vibration, sudden acceleration, and powerful acoustic forces. Voyager had to survive that initial chaos before it could even begin its scientific work. Engineers designed a rigid but lightweight framework, carefully balancing strength against mass. Too heavy, and the rocket could not carry it efficiently. Too light, and the structure might fail before reaching space. Materials were chosen not just for strength, but for predictability. Aluminium alloys, titanium components, and carefully tested fasteners were selected because their behavior under stress was well understood. Nothing exotic was allowed unless it had been proven beyond doubt. Reliability mattered more than novelty. Once beyond Earth, the stresses changed completely. Instead of vibration and heat, Voyager would face cold so intense that ordinary materials could become brittle. Temperatures could swing dramatically, depending on distance from the sun and orientation of the spacecraft. Some components would be exposed to sunlight, others would sit permanently in shadow. To cope with this, Voyager relied heavily on passive thermal control. Insulation blankets, reflective surfaces, and carefully placed louvers helped regulate temperature without moving parts. Heaters were included where necessary, but even those had to be used sparingly because every watt of power was precious. The goal was not comfort. It was survival within narrow margins. Radiation posed another problem. Beyond Earth's protective magnetic field, high-energy particles constantly stream through space. Over time, they damage electronics, corrupt data, and degrade materials. In the 1970s, radiation-hardened components were limited and expensive. Instead of trying to block radiation entirely, engineers focused on resilience. Critical systems were duplicated, some were triplicated. If one circuit failed, another could take over. Memory bits were protected with error-checking routines that could detect and correct mistakes caused by stray particles. The idea was not to prevent damage completely, but to ensure that damage would not be fatal. This approach extended to nearly every major subsystem. Voyager was designed with redundancy as a guiding principle. There were multiple attitude control thrusters, multiple communication pathways, and overlapping sensors. Even the scientific instruments were chosen so that partial failure would still leave meaningful data behind. Fault tolerance became a central concept. The spacecraft needed to recognize problems and respond without waiting for instructions from Earth. Communication delays made real-time control impossible. A malfunction could not be diagnosed quickly enough to save the mission if the spacecraft simply froze in place. To address this, Voyager was given a limited form of autonomy. It could monitor its own systems and make basic decisions. If it detected a serious fault, it could switch to a safe mode, shutting down non-essential systems and pointing its antenna toward Earth. This was not intelligence in the modern sense. It was a carefully designed set of rules, but those rules allowed the spacecraft to protect itself. Power generation was perhaps the most critical design choice of all. Solar panels were useless at the distances Voyager would travel. Beyond Jupiter, sunlight is too weak to provide reliable energy. Instead, the spacecraft relied on radioisotope thermoelectric generators, a technology already used on earlier missions but never for such a long duration. These generators produce electricity from heat released by radioactive decay. Inside each unit, pellets of plutonium dioxide slowly release energy as they decay naturally. That heat creates a temperature difference across thermocouples, which convert it directly into electrical current. There are no moving parts, nothing spins, nothing wears out in the conventional sense. The physics behind this process is simple but relentless. The amount of power produced decreases steadily over time, following the known decay rate of the fuel. Engineers could calculate decades in advance how much power would be available in any given year. They also knew it would never increase. This forced difficult choices. Instruments could not all remain active forever. Systems would eventually have to be turned off, one by one, as power declined. Voyager was designed with this future in mind. Engineers planned which components could be sacrificed first and which must be preserved for as long as possible. Communication presented its own challenges. Voyager needed to send data across distances that had never been attempted before. The solution was a large high-gain antenna fixed to the body of the spacecraft. Unlike steerable dishes on Earth, Voyager's antenna could not move independently. The entire spacecraft had to be oriented precisely to point the antenna back toward Earth. This imposed strict requirements on attitude control. Small thrusters, using hydrazine fuel, adjusted Voyager's orientation with careful bursts. These movements had to be precise and economical. Fuel could not be replenished. Every adjustment was a permanent cost. On Earth, communication depended on the Deep Space Network, a system of massive radio antennas located around the globe. These facilities were designed to transmit powerful signals outward and to listen for extremely weak ones returning. As Voyager moved farther away, the role of these antennas became increasingly important. Without them, the spacecraft would have been effectively silent long before reaching the outer planets. Computing constraints shaped the mission in subtle but profound ways. By modern standards, Voyager's computers were extraordinarily limited. Memory was measured in kilobytes. Processing speeds were slow. Programs had to be compact, efficient, and robust. There was no room for complexity. Software had to be written with absolute clarity. Every possible state had to be anticipated. Engineers could not rely on brute force computation. They relied on elegance. Simple algorithms, carefully tested, performed tasks that today would seem trivial, but at the time required extraordinary discipline. Even updating software after launch was a challenge. Changes had to be transmitted as sequences of commands, carefully verified before execution. A single mistake could have catastrophic consequences. Over time, engineers developed new techniques for working within these constraints, finding creative ways to extend the spacecraft's capabilities without rewriting its core systems. What emerged from all this was not a perfect machine, but a resilient one. Voyager was never invincible. It was vulnerable to radiation, to power loss, to mechanical wear. but it was designed to fail slowly rather than suddenly, to degrade gracefully rather than collapse. That philosophy proved essential. Unknown environments could not be simulated fully on Earth. No laboratory could recreate the combined effects of decades in deep space. The only way to learn was to send the spacecraft and see what happened. Voyager was built as an answer to that uncertainty, not by pretending the unknown could be controlled, but by accepting it and designing around it. Every redundant circuit, every backup mode, every conservative choice reflected a quiet confidence that while the future could not be predicted, it could be endured. In the end, the spacecraft became a product of restraint as much as ambition. It did not rely on cutting-edge technology that might fail unexpectedly. It relied on proven principles applied with extraordinary care. That care is what allowed it to keep going long after its designers expected it to stop. Voyager's endurance was not an accident. It was the result of hundreds of small decisions made by people who understood that once the spacecraft left Earth, it would have to carry their caution with it into the unknown. Launch day is often remembered as spectacle, but for Voyager it was more like a handoff, a long chain of planning, testing and anticipation, narrowed down to a short sequence of controlled events, each one pushing the spacecraft closer to a point where Earth would no longer be able to intervene. The launch vehicle chosen for this task was the Titan III E Centaur, one of the most powerful rockets available at the time. Power mattered, but precision mattered more. Voyager needed enough energy not just to rise above Earth, but to escape its gravitational grip entirely, and do so along a very specific path. Leaving Earth is not simply a matter of going upward. It is a matter of going sideways fast enough that gravity curves into a long fall that never quite lands. Earth's gravity well is deep. To climb out of it, a spacecraft must reach a speed where its forward motion continually misses the planet beneath it. This balance between speed and gravity defines orbit, and exceeding it defines escape. The rocket's job was to provide that excess energy cleanly, without shaking the spacecraft apart or nudging it off course. As the Titan stages ignited in sequence, Voyager was subjected to forces far more intense than anything it would experience afterward. Acceleration pressed components into their mounts. Vibrations rippled through the structure, yet all of this chaos was temporary. Within minutes, the final stage shut down, and silence replaced noise. That silence marked a transition. Voyager was no longer climbing, it was coasting. Separation from the rocket was the first true moment of independence. Once released, Voyager became a spacecraft in its own right, no longer attached to anything that could correct a mistake. From that instant forward, every adjustment had to be made using its own limited fuel and onboard systems. The initial trajectory was close to ideal, but not perfect. No launch ever is. Tiny deviations, invisible to the eye, can grow into enormous errors over millions of kilometers. This is why early trajectory correction maneuvers are critical. Small thruster burns, lasting only seconds, were used to fine-tune Voyager's path. These corrections relied on precision navigation. Engineers on Earth tracked the spacecraft using radio signals, measuring changes in frequency caused by motion. This Doppler tracking allowed them to determine Voyager's speed and direction with extraordinary accuracy. Combined with ranging measurements, it created a three-dimensional picture of where the spacecraft was and where it was heading. Navigation at this stage was as much art as science. Models accounted for gravitational influences from Earth, the Moon, the Sun, and even pressure from sunlight itself. Each correction was planned carefully, balancing the need for accuracy against the reality that fuel spent early could never be recovered later. As these maneuvers were completed, something subtle but important changed in how the mission was perceived. Voyager was no longer in a preparatory phase. It had crossed a threshold where recall was impossible. There was no scenario in which it could be brought back, serviced, or restarted. From this point on, every success and failure would be permanent. This required a psychological shift for the people involved. Engineers are trained to fix problems. Scientists are trained to adjust experiments. Voyager demanded restraint. Not every anomaly could be addressed immediately. Not every unexpected reading was a crisis. Learning when to intervene and when to wait became a skill in itself. Operational procedures evolved quickly. Teams learned to trust the spacecraft's autonomy. Commands were double-checked, then checked again. Simplicity became a virtue. The fewer instructions sent, the fewer opportunities for misunderstanding. Meanwhile, Voyager's instruments began to wake up. Initial activation followed a careful sequence. Power was distributed gradually. Sensors were tested one at a time. Telemetry streams were monitored for signs of stress or unexpected behavior. Temperatures, voltages, and data rates were compared against predictions made years earlier. These checks were not glamorous, but they were essential. Before Voyager could study planets or space itself, it had to prove that it could observe reliably. Each instrument that came online successfully represented another confirmation that the spacecraft was healthy. At the same time, distance began to make itself felt. Even in the early days after launch, communication delays were noticeable. Signals no longer arrived instantaneously. There was a pause between command and response. It was small at first, measured in seconds, but it grew steadily. This delay changed how control worked. Real-time steering was impossible. Instead, sequences of commands had to be planned in advance, transmitted, and then waited on. Engineers learned to think ahead, imagining where Voyager would be when instructions arrived rather than where it was when they were sent. This way of working demanded patience. It also demanded trust. Once a command left Earth, it could not be altered mid-flight. Voyager would execute it exactly as written, or not at all. As days passed and distance increased, Earth's presence faded in practical terms. The spacecraft no longer felt close. It existed in a different regime, where mistakes could take hours or days to reveal themselves. Silence between transmissions became normal rather than alarming. Yet throughout this period, Voyager performed exactly as designed. Systems remained stable. Navigation solutions converged. Instrument readings matched expectations. The spacecraft settled into the rhythm of long-distance travel. There is temptation to see launch as the dramatic climax of a mission. In reality, for Voyager, it was the quiet beginning of separation, the moment when preparation ended and commitment began. From that point forward, Voyager belonged more to space than to Earth. It would still listen. It would still respond. But every kilometre added to the distance made that relationship more abstract. Control became suggestion. Observation replaced intervention. The first departure was not marked by fireworks or celebration. It was marked by consistency, by signals arriving when expected, by numbers lining up with predictions, by a machine behaving exactly as it had been taught to behave. In that reliability lay the true success of launch. Voyager had not only escaped Earth's gravity, it had escaped Earth's immediacy. It was free to follow a path set years earlier, guided by physics rather than hands. And with that freedom came the beginning of a journey that could no longer be paused, revised, or undone. Once Voyager had escaped Earth, the challenge was no longer how to leave, but how to travel far enough to matter. Rockets are powerful, but they are blunt instruments. They burn fuel quickly and then fall silent. Carrying enough propellant to visit the outer planets directly would have made the spacecraft impossibly heavy. Instead, Voyager relied on something far more subtle and far more powerful: gravity itself. Every planet moves through space with enormous momentum. Jupiter alone outweighs all the other planets combined, and it moves around the Sun at tens of thousands of kilometers per hour. That motion represents stored energy on a scale no spacecraft could ever carry internally. The insight behind gravity assist was that a spacecraft does not need to bring all its own energy if it can borrow a small amount from a planet already in motion. The idea is often explained simply, but its implications are profound. As a spacecraft approaches a planet, it falls into the planet's gravitational field and accelerates. As it swings past, gravity bends its path. If the approach is timed correctly, the spacecraft leaves not just in a new direction, but at a higher speed relative to the Sun than it had before. The planet loses an immeasurably small amount of momentum. The spacecraft gains just enough to change its destiny. This exchange obeys conservation of momentum perfectly. Nothing is created. Nothing is violated. Energy is redistributed in a way that is entirely lawful and extraordinarily useful. For Voyager, gravity assist was not an optional enhancement. It was the mission. Without it, the spacecraft could have visited one planet and then coasted outward slowly. With it, Voyager could leap from world to world, each encounter adding speed and bending its trajectory toward the next target. This made the so-called grand tour of the outer planets possible, something that would otherwise have remained a mathematical curiosity rather than a real mission. Predicting these maneuvers required extraordinary precision. Long before launch, scientists calculated trajectories years into the future. They accounted for the masses of the planets, their velocities, their positions at specific times, and even subtle influences such as the pressure of sunlight on the spacecraft's surface. These calculations were performed using mathematics that had been refined over centuries, but applied at a scale few missions had ever attempted. In principle, the physics was clean. In practice, execution was delicate. A gravity assist is unforgiving. Arrive too early or too late and the angle is wrong. Pass too close and the spacecraft risks damage from radiation or atmospheric drag. Pass too far and the gravitational bend is too weak to matter. The margin for error is often measured in hundreds of kilometers, which sounds generous until it is compared to distances of hundreds of millions of kilometers. Navigation teams relied on constant tracking to refine Voyager's path. Radio signals sent from Earth bounced back, allowing engineers to measure tiny changes in frequency caused by motion. From these shifts, they inferred velocity and position with remarkable accuracy. Each update fed back into trajectory models, tightening predictions as the encounter approached. Even so, reality never matches mathematics perfectly. Planets are not smooth spheres. Their gravity fields are uneven, influenced by internal structure and rotation. Jupiter, in particular, is a complex gravitational environment with powerful radiation belts and a vast magnetic field. Voyager's passage through this region tested both prediction and resilience. What mattered most was timing. The outer planets were aligned in a configuration that would not repeat for well over a century. This alignment meant that after visiting Jupiter, Voyager could be bent towards Saturn. From Saturn, the path could be adjusted again, opening routes either deeper into the solar system or outward toward interstellar space. Miss one encounter, and the entire sequence would unravel. This made early decisions critical. Choices made during the first gravity assist constrained everything that followed. There was no opportunity to start over. The spacecraft could not slow down, turn around, and try again. Gravity assists are one-time events. They work because planets move. Once that moment passes, it is gone. Voyager's trajectory after Jupiter was shaped not only by where the planet was, but by where it would be years later. Engineers had to think in long arcs, imagining the spacecraft not as a point moving through space, but as a thread weaving between moving targets. This way of navigating marked a shift in planetary exploration. Earlier missions treated planets as destinations. Voyager treated them as partners in motion. Each world was both an object of study and a tool for reaching the next. The success of this approach reshaped mission design for decades to come. Later spacecraft would rely heavily on gravity assists, using Venus, Earth, and even the Moon to build energy gradually. What Voyager demonstrated was not just that gravity assists worked, but that they could be chained together reliably across vast distances and long timescales. There is a quiet elegance to this. Instead of overpowering the solar system with engines, Voyager learned to move with it. The spacecraft did not fight gravity, it listened to it. This listening required humility. Gravity assist trajectories leave little room for improvisation. Once set, they commit the mission to a particular future. Voyager's path after its planetary encounters was not chosen casually. It was the result of careful prioritization between scientific goals and long-term survival. In some cases, choosing one destination meant abandoning another. Visiting certain moons or planets would require passing too close, risking damage or altering the exit trajectory in ways that would prevent further encounters. Engineers had to decide what mattered most, knowing that each choice closed doors forever. These decisions carried consequences far beyond the immediate mission. The speed Voyager gained from its gravity assists eventually determined whether it would remain bound to the Sun or escape into interstellar space. That outcome was not a separate plan added later. It was baked into the early geometry of the mission. By the time Voyager left Saturn, much of its fate was already sealed. Its speed, direction, and long-term path were the cumulative result of gravitational nudges received years earlier. From that point on, the spacecraft was less a pilot than a passenger, carried forward by momentum it had carefully acquired. This is one of the less intuitive lessons Voyager offers. Control does not always mean constant adjustment. Sometimes it means choosing an initial path so carefully that little adjustment is needed later. Gravity assist reward foresight more than reaction. There is also something quietly human in this strategy. Voyager succeeded not by forcing the universe to comply, but by understanding how it already moves. It found leverage not in raw power, but in patience and timing. A spacecraft that relies on gravity assist must accept delays. It must wait for planets to be in the right place. It must travel indirect routes. In exchange, it gains access to distances that would otherwise be unreachable. For Voyager, that trade was worth everything. By using gravity as a tool rather than an obstacle, the mission expanded the map of what robotic exploration could achieve. It turned the solar system into a network of pathways rather than isolated points. It showed that with enough planning, a small machine could ride the motions of worlds and reach the edge of the Sun's influence. The consequences of those early gravitational choices continue to unfold. Long after the engines fell silent, the borrowed momentum carries Voyager onward. Every kilometre it travels today is the result of decisions made decades ago, when gravity was treated not as a barrier, but as an ally. In that sense, Voyager's journey is not powered by fuel anymore. It is powered by understanding. Jupiter was the moment when Voyager stopped being a promise and became a discovery machine. Until then, the spacecraft had been travelling through emptiness, guided by calculations and expectation. Jupiter changed that. It was no longer a point of navigation or a source of borrowed momentum. It was a world, vast and active, filling the instruments with more information than engineers had ever received from a single planetary encounter. Even from a distance, Jupiter dominated the field of view. It is the largest planet in the solar system, more massive than all the others combined, and its influence extends far beyond its visible disk. As Voyager approached, the planet's gravity began to tug noticeably on the spacecraft's trajectory. The Sun was no longer the only authority. Jupiter announced itself early. The first images returned were already different from anything seen before. Ground-based telescopes had shown Jupiter as a banded globe, striped with light and dark clouds. Voyager's cameras revealed complexity layered on top of that familiarity. The cloud bands were not smooth, they were turbulent, folded, and alive with motion. Storms of different sizes interacted, merged, and tore at one another in ways that suggested an atmosphere driven by immense internal energy. The most famous feature, the Great Red Spot, had been observed for centuries. Voyager showed it in detail that transformed understanding. It was not a static mark, but a vast rotating storm system, large enough to swallow Earth, with structure extending deep into the atmosphere. Smaller storms orbited it, filaments wrapped around its edges. The planet's atmosphere behaved less like a painted surface and more like a living fluid. These observations reshaped ideas about atmospheric dynamics. Jupiter does not receive much energy from the Sun compared to Earth. Instead, it generates heat from within. Voyager's data supported this, revealing convection patterns driven by internal warmth rather than surface heating. The planet's weather was not seasonal in the way Earth's is. It was continuous, powerful, and largely independent of sunlight. But Jupiter itself was only part of the story. As Voyager turned its attention to the planet's moons, something entirely unexpected appeared. Io, one of the 4 large moons discovered by Galileo centuries earlier, had long been assumed to be a dead, cratered world like Earth's moon. Instead, Voyager found it actively erupting. Plumes rose hundreds of kilometers above Io's surface. Material arced outward and fell back, reshaping the landscape in real time. These were volcanoes, not frozen relics, but ongoing geological processes. Io became the first place beyond Earth where active volcanism was directly observed. This discovery forced a rethinking of how moons behave. Io is relatively small. It should have cooled and solidified long ago. The explanation lay in gravity. Io is locked in a gravitational dance with Jupiter and neighbouring moons. As it orbits, Jupiter's immense gravity stretches and compresses it rhythmically. This constant flexing generates heat through friction within the moon's interior. This process became known as tidal heating. Voyager did not invent the concept, but it provided the clearest evidence that gravity alone could power geology. Heat did not require radioactive decay or leftover formation energy. It could be generated simply by motion and distortion. This insight would later influence thinking about moons elsewhere in the solar system, including those thought to harbour subsurface oceans. Jupiter's magnetic environment proved just as dramatic. Voyager detected a magnetic field far stronger than Earth's, extending millions of kilometers into space. This field traps charged particles, creating radiation belts intense enough to damage electronics and pose serious risks to spacecraft. The instruments measured particle densities and energies that exceeded expectations. Jupiter's magnetosphere behaved like a miniature version of the Sun's influence, dominating space around the planet. Its interaction with the solar wind formed shock fronts and boundary regions that mirrored processes seen on much larger scales. These measurements had immediate practical consequences. Engineers adjusted spacecraft operations to protect sensitive systems during the closest approach. Instruments were powered down selectively. Orientation was controlled carefully. The encounter tested Voyager's resilience in ways no simulation could fully capture. Scientifically, the magnetic data offered insight into Jupiter's interior. A strong magnetic field implies a conductive, moving layer beneath the surface. The leading explanation involved liquid metallic hydrogen, a state of matter that forms only under extreme pressure. Voyager's measurements strengthened this idea, suggesting that Jupiter's interior is unlike anything found on Earth. The planet's ring system also emerged from obscurity. Jupiter's rings are faint and thin, invisible from Earth. Voyager detected them indirectly at first, then confirmed their presence through imaging. Their discovery hinted that rings might be more common than previously thought, not unique to Saturn. Together, these observations began to reshape models of planetary formation. Jupiter was no longer just a gas giant that failed to become a star. It was a dynamic system, with complex interactions between atmosphere, moons, magnetic fields, and surrounding space. Its influence extended far beyond its visible boundaries, shaping the entire region. The sheer volume of data returned from the encounter overwhelmed expectations. Instruments performed better than hoped. Images arrived crisp and detailed. Measurements aligned with theory in some places and challenged it in others. For the first time, the mission felt unquestionably real. There was a shift in tone among scientists and engineers. Before Jupiter, the mission has been cautious. After Jupiter, it became confident, not reckless, but assured. Voyager had proven itself capable not just of surviving, but of transforming understanding. This confidence mattered because the mission was far from over. Jupiter was the first test of everything Voyager was meant to do. Navigation, communication, power management, and scientific observation all had to work in concert. They did. The encounter also changed how future missions would be planned. Jupiter was revealed as both a scientific treasure and a hazardous environment. Any spacecraft venturing there would need to respect its radiation, its gravity, and its scale. Voyager provided the map. There was also a subtler change. Up to this point, Voyager had been following a plan. At Jupiter, it began to reveal the limits of planning. Nature offered surprises that no committee could predict. Volcanoes on Io were not on the checklist. The complexity of the magnetosphere exceeded expectations. The atmosphere behaved in ways that demanded new models. This is where exploration becomes discovery. As Voyager receded from Jupiter, the planet shrank back into a point of light, but its impact lingered. The data continued to arrive long after closest approach. Scientists spent years analyzing it, and many are still doing so. Jupiter was not a chapter to be closed, it was a foundation. Perhaps most importantly, Jupiter validated the mission's core idea, that sending a machine far away and letting it observe patiently could reveal processes impossible to infer from a distance, that the solar system was not static, but active, that even the largest planets were not simple. By the time Voyager left Jupiter's influence behind, it carried more than momentum. It carried proof. Proof that the long journey was worth it. Proof that the unknown was not empty. Proof that careful engineering paired with curiosity could turn a flyby into a revolution in understanding. Jupiter was the first place where Voyager truly met another world, and it did not disappoint. Saturn arrived not as a single object, but as a system. From a distance it appeared serene, almost delicate, its pale rings encircling a softly banded globe. Up close, that calm appearance dissolved into structure, motion, and interaction on every scale. Where Jupiter had revealed power through turbulence and intensity, Saturn revealed complexity through order. As Voyager approached, the rings became the dominant feature. From Earth, they appear smooth and continuous, like solid bands. Voyager showed something entirely different. The rings were made of countless individual particles, ranging in size from fine grains to chunks as large as houses. Each piece followed its own orbit, governed by gravity, collisions, and subtle resonances. The structure was astonishingly intricate. Narrow gaps sliced through the rings. Some were clean and sharply defined. Others were braided, wavy, or filled with faint material. Voyager's instruments revealed that the rings were not static. They were dynamic, constantly reshaped by interactions between particles and by the gravitational influence of nearby moons. These gaps were not empty by accident. Many were maintained by small moons, later called shepherd moons, whose gravity nudged ring particles into precise arrangements. As a moon passed nearby, it could pull particles inward or push them outward, clearing a lane or creating waves that propagated through the ring material. Gravity, once again, acted not as a blunt force, but as a sculptor. The physics behind this behavior was subtle but elegant. When a ring particle's orbital period formed a simple ratio with that of a moon, repeated gravitational tugs occurred at the same point in its orbit. Over time, those nudges accumulated, moving particles away from unstable regions. This process explained why some gaps were so sharply maintained and why the rings displayed repeating patterns. Saturn's rings became a natural laboratory for studying orbital mechanics. Processes that also shape galaxies, planetary disks, and even protoplanetary systems could be observed here in miniature. Voyager transformed the rings from a visual curiosity into a physical system governed by measurable rules. Beyond the rings, Saturn's moons offered their own surprises. Titan, the largest, quickly became a focal point. Ground-based observations had hinted at an atmosphere, but Voyager confirmed it beyond doubt. Titan was shrouded in a thick, hazy envelope that completely obscured its surface. This atmosphere was rich in nitrogen, with complex organic molecules suspended in its upper layers. Voyager's instruments detected chemistry driven by sunlight interacting with methane, producing a smog-like haze that coated the moon. Titan immediately stood out as unique. No other moon observed so far had such a substantial atmosphere. The discovery raised profound questions. An atmosphere implies active processes. It implies weather, circulation, and chemical evolution. Titan's temperature was far too low for liquid water, but its chemistry hinted at pathways that might resemble early stages of prebiotic processes. While Voyager could not see the surface, it revealed a world that demanded future exploration. Other moons added to the picture. Some showed heavily cratered surfaces suggesting ancient inactive histories. Others appeared smoother, hinting at resurfacing processes. The diversity among Saturn's moons suggested that size alone did not determine a moon's fate. Location, composition, and gravitational interactions mattered just as much. Saturn itself proved no less complex. Voyager's images revealed atmospheric bands similar to Jupiter's, but more subtle. The colours were muted. The contrasts were softer. Yet beneath this gentler appearance lay powerful winds. Measurements showed jet streams encircling the planet, some reaching speeds comparable to those seen on Jupiter. The atmosphere displayed layered cloud structures, with hazes at high altitude and denser clouds below. Storm systems appeared and dissipated. Unlike Earth, where weather is driven primarily by sunlight, Saturn's atmosphere is influenced strongly by internal heat. The planet radiates more energy than it receives from the Sun, a clue to ongoing processes deep within. Voyager's observations refined models of gas giant atmospheres. Saturn was not simply a scaled-down Jupiter. Differences in composition, rotation rate, and internal structure produced distinct behaviors. Comparative planetology emerged more clearly here, using one world to understand another. All of this science unfolded while another critical task was underway. Saturn was not only a destination, it was a pivot point. The gravity assist at Saturn would determine Voyager's future. Engineers had to choose between different trajectories. One path would send the spacecraft toward Uranus and Neptune. Another would fling it upward, out of the plane of the solar system toward interstellar space. The decision depended on timing, geometry, and risk. Passing close to Saturn carried hazards. The rings themselves posed a danger. Even a small particle striking at high speed could be catastrophic. Careful planning ensured that Voyager passed through a region where ring material was sparse, threading a gravitational needle with precision. This encounter refined gravity assist techniques even further. Saturn's mass and ring system created a complex environment. Tiny differences in approach angle translated into large differences in exit trajectory. Engineers adjusted the spacecraft's path with exquisite care, knowing that once the encounter was complete, the outcome could not be changed. The success of the Saturn flyby demonstrated a new level of confidence. Voyager had now navigated two massive gravitational encounters without incident. It had returned unprecedented scientific data. It had survived radiation, dust, and the mechanical stresses of long travel. Saturn also reinforced an emerging lesson. Planets are not isolated objects. They are centers of systems, influencing and shaped by their surroundings. Rings, moons, magnetic fields, and atmospheres interact continuously. To understand a planet, one must understand everything around it. By the time Voyager departed Saturn, the rings had receded into a thin line, and the planet itself shrank into a pale dot. Yet the data gathered there would occupy scientists for decades. Ring dynamics informed theories of disk evolution. Titan's atmosphere became a touchstone for studies of organic chemistry in cold environments. Saturn's weather refined atmospheric models across the solar system. Perhaps most importantly, Saturn marked a point of no return in another sense. After this encounter, Voyager's mission diverged from what had originally been imagined. The spacecraft had outperformed expectations. It had justified its existence many times over. Saturn showed that exploration does not simply add facts, it reorganizes understanding. A planet once admired mainly for its beauty became a complex system, governed by physical laws that echo across the universe. And with that understanding secured, Voyager continued outward, carrying with it a deeper appreciation of how structure emerges from gravity, motion, and time. For a time, Voyager was not one story but two machines sharing the same ambition. Launched weeks apart, Voyager 1 and Voyager 2 were designed as near twins, built to explore the outer planets using the same principles, the same instruments, and much of the same planning. Early in the mission, their paths felt parallel. They were separated in space, but united in purpose. That unity did not last. The divergence was not the result of malfunction or accident. It was deliberate, calculated, and rooted in a central tension that defines all exploration. You cannot go everywhere. Every choice opens one path and closes another. By the time the spacecraft approached Saturn, engineers and scientists faced a decision that could not be postponed. The geometry of gravity assists meant that only one future could be chosen for each craft. The same planetary encounter could not serve every possible goal. The solar system does not offer unlimited flexibility. It offers brief windows. The key question was scientific priority. At the time, Saturn's moon Titan was considered one of the most intriguing objects in the outer solar system. It was large, dense, and shrouded in a thick atmosphere. Understanding Titan meant understanding how atmospheres form and persist far from the Sun. It also meant probing chemistry that could not be studied anywhere else. To study Titan properly, Voyager needed to pass close, very close. That approach angle, however, came with a cost. A close flyby of Titan would bend the spacecraft's trajectory sharply, tilting it out of the plane of the solar system and sending it on a fast path toward interstellar space. That path would make visits to Uranus and Neptune impossible. The alternative was restraint. A more distant flyby would preserve a flatter trajectory, allowing the spacecraft to continue onward to the ice giants. That option promised breadth, rather than depth. More planets, but fewer details at Saturn's most enigmatic moon. This was not a purely technical decision. It was philosophical. Should the mission focus on a single extraordinary target or spread its reach across as many worlds as possible? Should it prioritize atmosphere over geography, chemistry over cartography? The answer was compromise. Voyager 1 was assigned the Titan encounter. Voyager 2 was given the longer road. This decision immediately broke the symmetry between the spacecraft. From that moment on, they were no longer interchangeable. They were no longer backups for one another. Each carried a distinct responsibility. For Voyager 1, the close pass by Titan came with an energetic reward. Saturn's gravity, combined with the specific geometry of the encounter, accelerated the spacecraft to a higher speed relative to the Sun than any previous mission. It was not just leaving Saturn, it was being flung outward. That increase in speed mattered enormously. It meant that Voyager 1 would reach the outer boundary of the solar system sooner. It would encounter regions of space that no spacecraft had sampled before, and it would do so while its instruments were still relatively young. Voyager 2, by contrast, followed a more measured path. Its trajectory after Saturn was designed to intersect Uranus and Neptune, worlds that had never been visited by a spacecraft. That choice required careful conservation of energy. Speed had to be managed rather than maximized. The spacecraft needed just enough momentum to continue outward without overshooting its future targets. This difference in energy profiles shaped everything that followed. For Voyager 1, Saturn marked the beginning of a long departure. Its encounters ended sooner, but its journey outward accelerated. For Voyager 2, the mission expanded. It would spend more years navigating the outer solar system, collecting planetary data at the cost of reaching deep space later. The implications were clear even at the time. Voyager 1 would become the first human-made object to leave the influence of the Sun. Voyager 2 would become the most travelled planetary explorer in history. Neither outcome was considered superior. They were complementary. The loss of symmetry between the spacecraft also changed how the mission was managed. Engineers could no longer apply the same strategies to both. Power budgets diverged. Instrument usage schedules differed. Even communication priorities shifted as their distances and scientific roles separated. There was also a psychological adjustment. Redundancy, once a comfort, faded. If one spacecraft encountered trouble, the other could no longer easily replicate its science. Each failure would be permanent. Each success would be unique. The moment Voyager 1 began its faster exit was not dramatic. There was no visible marker, no announcement. It happened quietly, encoded in the geometry of its Saturn flyby. From that point on, its velocity relative to the Sun was sufficient to ensure that it would never return. The path forward was irreversible. This is an important aspect of deep space exploration. Trajectories are not easily changed once energy is added. A spacecraft that gains too much speed cannot simply slow down without fuel it does not have. Momentum is generous when acquired, but unforgiving when lost. For Voyager 1, this meant that its future became simpler in some ways and more profound in others. There would be no more planets, no more close encounters. The mission shifted from planetary science to something quieter, measuring space itself. For Voyager 2, complexity increased. Each additional planetary encounter required new navigation solutions, new risk assessments, and new patience. Its journey would be longer, its challenges more varied. Looking back, this divergence illustrates a broader truth about exploration. Missions are shaped as much by what they abandon as by what they pursue. Voyager's twin paths demonstrate how scientific goals can diverge without conflict, each revealing different aspects of the same system. One spacecraft prioritized depth at Saturn and speed thereafter. The other prioritized breadth across the outer planets. Together, they provided a fuller picture than either could alone. The decision also revealed something about confidence. By the time of the Saturn encounter, Voyager had proven itself robust enough to justify bold choices. Engineers trusted the spacecraft to survive close approaches and long journeys alike. Scientists trusted the data to be worth the risk. This trust was not blind. It was earned through performance. As Voyager 1 accelerated outward, its identity began to change. It was no longer defined by what it would visit next, but by what it would eventually reach. Its path pointed away from familiar landmarks toward regions defined only by models and theory. Voyager 2, meanwhile, continued to follow a more traditional arc of exploration, moving from one world to the next, extending the map of known planetary environments. The divergence was not a split so much as a branching. Two futures unfolding from a single origin. Two ways of learning about the solar system, both valid, both necessary. In the end, the choice made at Saturn ensured that Voyager would not tell one story, but two. One about the richness of planetary systems, another about the nature of space beyond them. And both stories began with the same moment, a decision to accept that you cannot go everywhere, and that choosing carefully can take you farther than trying to do everything at once. Uranus entered the story quietly, almost awkwardly, as though it had been waiting its turn without much expectation of attention. Before Voyager, it was the least understood of the classical planets. A pale blue disk seen through telescopes, distant and featureless. It had been discovered almost by accident centuries earlier and, until a spacecraft arrived, had remained largely theoretical in character. Voyager's encounter transformed that abstraction into a place. The first and most striking revelation was orientation. Uranus does not spin like the other planets. Instead of rotating upright with a modest tilt, it lies almost on its side. Its axis is tipped by roughly 98 degrees, meaning that for much of its long year, one pole faces the sun continuously, while the other remains in darkness. Voyager's images made this geometry unavoidable. The planet did not just look different, it behaved differently. This extreme tilt has profound consequences. Seasons on Uranus are not gentle transitions, they are prolonged extremes. Each pole experiences decades of continuous daylight followed by decades of night. Voyager arrived during a period when one hemisphere was illuminated almost constantly. The sun hovered near one pole, casting long shadows across the planet's upper atmosphere. This raised immediate questions. How does an atmosphere respond to such conditions? On Earth, seasonal changes are moderated by oceans and rapid rotation. On Uranus, rotation is fast, but solar input is wildly uneven over time. Voyager's measurements suggested that despite these extremes, the atmosphere was surprisingly calm. Winds were present, but not as violent as those on Jupiter or Saturn. Temperature differences were muted. This calmness puzzled scientists. One might expect dramatic contrast between sunlit and dark regions. Instead, Uranus appeared thermally uniform. This hinted at efficient heat redistribution, or at internal processes dominating over solar heating. Either way, Uranus challenged assumptions about how atmospheres behave. The planet's magnetic field added another layer of strangeness. Unlike Earth's relatively well-aligned magnetic field, Uranus's field is tilted significantly relative to its rotation axis and offset from the planet's center. Voyager's instruments detected a magnetosphere that wobbled and twisted as the planet rotated. This misalignment suggested an internal structure unlike that of Jupiter or Saturn. Instead of a large region of metallic hydrogen generating the field, Uranus likely produces its magnetism in a shell of electrically conducting fluid composed of water, ammonia, and other compounds under extreme pressure. This insight reshaped thinking about how magnetic fields can arise, broadening the range of possible planetary interiors. The magnetosphere itself was dynamic and asymmetric. As Uranus rotated, its magnetic field swept through space in a corkscrew pattern, interacting with the solar wind in complex ways. This created a magnetospheric environment unlike any previously observed. Voyager provided the first direct measurements, opening an entirely new category of planetary magnetism. Uranus's moons also defied expectations. Voyager discovered new moons and revealed surprising diversity among those already known. Some were heavily cratered, bearing the marks of ancient impacts. Others showed signs of resurfacing, with smoother terrains hinting at geological activity long after formation. The moons were not uniform spheres. Many were irregularly shaped, suggesting that they had not fully differentiated or that they had experienced disruptive collisions. Their surfaces varied in brightness and texture, indicating differences in composition and history. Even within a single planetary system, Uranus offered variety rather than repetition. One moon in particular, Miranda, stood out. Its surface appeared like a patchwork stitched together from mismatched pieces. Steep cliffs rose abruptly. Grooves and ridges cut across the terrain. The scale of these features was startling. Voyager's images suggested a history of intense geological disruption, possibly driven by tidal heating or catastrophic impacts. Miranda became a reminder of how little could be inferred from distance alone. Before Voyager, it was just a point of light. Afterward, it was a world with a complicated past. The atmosphere of Uranus, though visually subdued, revealed subtle complexity. Voyager detected methane in the upper layers, which absorbs red light and gives the planet its blue-green colour. Beneath this haze lay deeper clouds composed of different compounds, arranged in layers that reflected temperature and pressure changes with altitude. Despite the planet's extreme tilt, Voyager observed few dramatic storms. This again challenged expectations. The atmosphere seemed restrained, as if internal heat sources were weak or deeply buried. Uranus emits very little excess heat compared to the energy it receives from the Sun, unlike Jupiter and Saturn, which glow with internal warmth. This lack of internal heat became one of Uranus's defining characteristics. It suggested a different formation history, or a unique evolutionary path. Perhaps heat escaped early. Perhaps internal layering inhibits convection. Voyager's brief visit could not answer these questions, but it framed them sharply. Time was Voyager's greatest limitation at Uranus. The encounter was fast. The spacecraft had only a narrow window to collect data. There was no opportunity to linger, to observe long-term changes, or to adjust plans based on early findings. Every instrument had to perform flawlessly on schedule. Despite this, the scientific return was immense. Voyager redefined Uranus from a pale curiosity into a complex dynamic system. It showed that even planets of similar size and composition can behave very differently depending on their history and structure. The encounter also highlighted a humbling truth. One flyby can transform understanding, but it cannot complete it. Uranus left scientists with more questions than answers. Why is its tilt so extreme? Why is its internal heat so low? How do its seasons truly affect its atmosphere over decades? Voyager could only offer a snapshot, but that snapshot was enough to demand further study. In moving beyond the familiar giants, the mission encountered a world that resisted simple classification. Uranus was not merely a smaller Jupiter or a colder Saturn. It was something distinct, shaped by an unusual past and governed by rules that only partially overlapped with those of its neighbours. The sideways planet expanded the catalogue of what planets can be. It showed that the solar system contains not just variations on a theme, but entirely different compositions and histories coexisting within the same gravitational family. As Voyager departed Uranus, the planet slipped back into obscurity, its secrets only partially revealed. Yet the brief encounter permanently altered how it was understood. Uranus was no longer an afterthought. It was a challenge. In that sense, the sideways world fulfilled one of exploration's quiet purposes. It reminded scientists that familiarity breeds assumptions, and that the universe has no obligation to conform to them. Neptune marked the far edge of the familiar solar system, the last planet Voyager would ever visit, and the final opportunity to turn distant theory into direct observation. Before the encounter, Neptune existed mostly as a prediction refined by mathematics and telescope work. Its position had been calculated long before it was seen, inferred from gravitational effects rather than light. Voyager's arrival transformed that abstract certainty into a physical place. From the first images, Neptune contradicted expectations. Despite its distance from the Sun, the planet was anything but quiet. Its atmosphere was alive with motion. Bright clouds streaked across a deep blue disk. Dark storm systems appeared and evolved over time. One of these, later called the Great Dark Spot, rivaled Earth in size and moved through the atmosphere with surprising speed. Measurements revealed wind velocities exceeding anything seen elsewhere in the solar system. Some atmospheric flows reached thousands of kilometers per hour, faster than those on Jupiter or Saturn. This was puzzling. Neptune receives very little solar energy. Sunlight at that distance is weak and diluted. Yet the atmosphere behaved as though powered by a strong internal engine. Voyager's data confirmed that Neptune emits more heat than it receives from the Sun. This internal heat source drives convection and fuels the planet's violent weather. The contrast with Uranus was striking. Two planets similar in size and composition, yet one quiet and restrained, the other energetic and turbulent. Neptune forced scientists to reconsider simple models of planetary evolution. The atmosphere itself showed layered complexity. High-altitude clouds composed of methane ice reflected sunlight brightly. Beneath them lay deeper cloud decks and hazes, shaped by temperature gradients and chemical processes. Voyager's instruments tracked these features as they shifted, merged, and dissipated, offering a glimpse of a living system rather than a frozen world. Neptune's rotation played a role as well. The planet spins relatively quickly, contributing to strong Coriolis effects that organize winds into bands and vortices. Combined with internal heat, this produced an atmosphere that seemed constantly in motion, even at the edge of the Sun's reach. If Neptune itself was surprising, its moon Triton was astonishing. Triton orbits Neptune in the opposite direction to the planet's rotation. This retrograde orbit immediately suggested that Triton did not form alongside Neptune. Instead, it was likely captured long after the planet's formation. Such a capture would have been violent, reshaping the moon's interior and surface. Voyager's images revealed a surface unlike any previously seen. Triton appeared young and lightly cratered, implying recent resurfacing. Even more remarkable were plumes rising from the surface, dark streaks blown across icy plains. These were geysers, ejecting nitrogen gas and dust into the thin atmosphere. This cryovolcanism showed that Triton was active despite its extreme cold. The energy driving these eruptions likely came from a combination of internal heat and seasonal sunlight. Triton's surface temperature is among the lowest measured in the solar system, yet it remained dynamic. The discovery of active geology so far from the Sun expanded the definition of what it means for a world to be alive, at least geologically. Heat did not have to come from proximity to a star. It could be generated through gravitational interactions, radioactive decay, or residual energy from formation and capture. Triton's atmosphere, though thin, added another layer of intrigue. Voyager detected nitrogen gas and traces of methane, cycling between surface and atmosphere as temperatures changed. This seasonal exchange blurred the line between solid and gas, reminding scientists that phase changes are not limited to warm environments. Together, Neptune and Triton completed the planetary survey that Voyager had set out to accomplish. From gas giants to ice worlds, the mission had revealed a solar system more varied and active than imagined. Reaching Neptune was not easy. By this point, Voyager was operating at extreme distance. Signals took hours to travel between Earth and the spacecraft. Navigation required exquisite precision. Small errors early in the mission could have resulted in missing the planet entirely. Engineers relied on careful tracking and incremental corrections to guide Voyager into position. Every adjustment consumed fuel that could never be replaced. Decisions were conservative. There was no room for improvisation. By the time Voyager reached Neptune, much of its path had been fixed years earlier. This made the encounter feel different from those before it. There was a sense of finality. Neptune was the last stop. After this, there would be no more chances to refine planetary science through close observation. Whatever Voyager gathered here would have to be enough. The emotional weight of this moment was real, even if rarely stated outright. For scientists who had worked on the mission for decades, Neptune represented both a culmination and a farewell. The spacecraft had exceeded expectations again and again. Now it was about to leave the planetary stage entirely. Yet the tone was not one of loss. It was one of completion. Voyager had done what it was built to do, and more. It had revealed the outer planets as complex systems shaped by internal energy, gravity, and time. Neptune was not an endpoint so much as a confirmation that the journey had been worthwhile. As Voyager departed Neptune, it did so at increased speed, guided once more by gravity. The planet's mass bent the spacecraft's path upward, tilting it out of the plane of the solar system. From this point on, Voyager would no longer encounter planets. It would travel through regions defined not by worlds, but by space itself. Scientifically, Neptune provided closure. Models of planetary atmospheres could now be tested across a wide range of conditions. The role of internal heat became clearer. The diversity of moon systems challenged assumptions about formation and capture. The solar system emerged not as a tidy sequence, but as a collection of individual histories bound together by gravity. There was also a quieter significance. Neptune represented the limit of what had once been visible to unaided human observation. Beyond it lay only darkness and theory. Voyager crossed that boundary with data still flowing, instruments still working, and momentum still carrying it outward. The last flyby was not marked by celebration. It was marked by continued transmission, by numbers arriving on screens, by images resolving and then fading as distance increased. The spacecraft did not pause. It did not turn back. It simply continued along a path set long ago. Neptune closed one chapter of exploration and opened another that no one could yet fully describe. The planetary realm had been surveyed. The solar system, in its classical sense, was complete. Beyond that lay something else, not empty but unfamiliar, and Voyager was already on its way there. By the time Voyager left the last planet behind, it had already transformed science. Yet attached to the side of the spacecraft was something that served no scientific function at all. It did not measure particles, it did not image clouds, it did not transmit data. It simply travelled. The golden record was never meant to help Voyager do its job. It was meant to say something about who sent it. The idea emerged quietly, almost as an afterthought during the planning stages of the mission. If a spacecraft was going to leave the solar system and wander through interstellar space indefinitely, perhaps it should carry something more than instruments and hardware. Perhaps it should carry a trace of its origin. This was not the first time such an idea had appeared. Earlier spacecraft had carried plaques bearing simple diagrams of human figures and the position of the sun among nearby stars. Those messages were minimal, almost abstract. The golden record was different. It was ambitious. It attempted not just to announce existence, but to offer context. At its core, the record was a phonograph disc made of gold-plated copper. Gold was chosen not for beauty, but for chemistry. It does not corrode easily. It resists oxidation. In the vacuum of space, shielded from moisture and atmosphere, it could remain intact for millions, perhaps billions of years. The record was designed to survive long after Voyager itself could no longer function. The physics of that durability mattered. Space is harsh in many ways, but it is also gentle in others. There is radiation, yes, and occasional impacts from dust. But there is no weather, no erosion by wind or water, no biological decay. A solid object drifting between stars can persist almost unchanged for timescales that dwarf human history. The golden record was built with that in mind. It was enclosed in an aluminium cover, engraved with instructions explaining how to play it and how to decode its contents. Those instructions relied on universal physical principles, such as the properties of hydrogen atoms and the nature of time derived from atomic transitions. The hope was not certainty, but intelligibility. The content of the record was curated carefully and controversially. A team of scientists, artists, and thinkers selected sounds, images, and music intended to represent Earth and its inhabitants. Greetings were recorded in dozens of human languages. The sounds of everyday life were included: footsteps, wind, rain, heartbeats. The intention was to convey not achievement, but presence. Music occupied a large portion of the record. Pieces were chosen from many cultures and eras, ranging from traditional folk songs to classical compositions. The selection was not meant to define excellence. It was meant to demonstrate diversity. Rhythm, melody, and harmony were treated as expressions of pattern rather than preference. Images were encoded as analog signals, capable of being reconstructed visually by anyone who understood the playback method. These images depicted basic scientific concepts such as anatomy and mathematics, alongside scenes of human life and natural landscapes. The goal was to move from the universal to the particular, from physics to biology, from biology to society. This raised immediate questions. Who gets to choose what represents humanity? Whose voices are included and whose are not? These debates were not hypothetical. They were active and often uncomfortable. Some argued that the record was too optimistic, too sanitized. Others worried it was too revealing. Still others questioned the premise entirely. Was it appropriate to send messages into space at all? Should a scientific mission carry cultural baggage? The answers were never unanimous. In the end, decisions were made under time pressure and with limited consensus. The record reflects those constraints. It is not a complete portrait of Earth. It is a snapshot filtered through the values and assumptions of a particular moment in history. That moment was the late 1970s, a period shaped by Cold War tension and scientific idealism. The Golden Record carries traces of both. It emphasizes cooperation, curiosity, and shared humanity, even as the world that produced it was deeply divided. In that sense, it is aspirational rather than descriptive. From a scientific perspective, the record was also an experiment in communication. It tested whether complex information could be encoded in a form that might be deciphered by an intelligence with no prior exposure to human culture. This required stripping concepts down to fundamentals: frequency, time, scale, proportion. There was no guarantee that any of it would be understood. The creators of the record knew this. The message was sent not because success was likely, but because the cost of sending it was small compared to the scale of the mission. Voyager would travel anyway. The record would simply come along. This is where meaning enters quietly. The Golden Record does not assume an audience. It does not expect to be found. Its journey is passive. It drifts with the spacecraft, indifferent to whether anyone ever notices it. In that way, it mirrors Voyager itself, which measures and transmits without regard for who listens. Yet the presence of the record changes how the mission is perceived. Voyager is no longer just a tool. It becomes a messenger, even if the message is never received. This dual identity has led to misunderstandings. The Golden Record is often described as a greeting to extraterrestrials, but that framing exaggerates intent. It was never a broadcast. It was a bottle cast into a cosmic ocean, sealed and sent without expectation of reply. The record's greatest audience has always been human. Its existence invites reflection. What would someone learn about Earth by listening to this disc? What would they miss? The answers reveal as much about the creators as about the planet. The choices made, the compromises accepted, the voices prioritized, all speak to the values of the time. As an artifact, the Golden Record is inseparable from its era. It reflects a belief that knowledge is worth sharing, that culture has structure, that meaning can be encoded. These beliefs are not universal. They are philosophical positions rooted in a particular scientific worldview. There is also something quietly humorous in the ambition of it all. A civilization still struggling to communicate with itself decided to leave a message for the universe. A species unsure of its future created an object designed to outlast it. The contrast is not tragic, it is human. From a purely physical perspective, the record is likely to outlive Earth's current geography. Continents will shift, oceans will open and close, the sun will brighten. Long before any of that threatens Voyager, the record will still be drifting unchanged, carrying sounds of rain and greetings spoken in a voices long silent. Whether it is ever encountered is almost irrelevant. Its significance lies in the act of creation rather than reception. The Golden Record represents a moment when science paused to acknowledge that exploration is not only about accumulation of data, but about expression of identity. Voyager would have been extraordinary without it. The record does not add to the mission's measurements, it adds context. It reminds listeners that behind the equations and engineering were people making choices about what mattered. In the vast silence beyond the planets, Voyager carries both information and intention. One is constantly transmitted and fades with distance. The other remains sealed, waiting, unconcerned with time. Together they form a quiet statement, not of conquest, not of warning, simply of presence. Something from Earth passed this way. Leaving the solar system is not a dramatic event. There's no clear line to cross, no final planet to wave goodbye to, no sudden change in scenery. Instead, it is a gradual transition, defined less by distance than by influence. Voyager's journey beyond the planets marked a shift from studying worlds to studying the space shaped by the sun itself. At the heart of this region is the solar wind. The sun does not simply emit light and heat. It constantly releases a stream of charged particles, mostly electrons and protons, flowing outward in all directions. This outflow carries the sun's magnetic field with it, stretching it into space and forming a vast protective bubble known as the heliosphere. The heliosphere is not empty. It is filled with this moving plasma, expanding outward until it encounters resistance from the surrounding interstellar medium. For decades after launch, Voyager remained well inside this solar influence. Even far beyond the orbit of Neptune, the sun still dominated the local environment. Understanding this region required a different kind of science. Planets are solid targets. Their properties are stable over short timescales. The heliosphere, by contrast, is fluid and dynamic. Its shape changes in response to solar activity and to the pressure exerted by interstellar space. Voyager's instruments were not just measuring where it was, but what kind of space it was in. As Voyager moved farther from the sun, the solar wind began to slow. Close to the sun, the wind travels at hundreds of kilometers per second. Farther out, as it expands and encounters resistance, that speed decreases. The point where the solar wind slows from supersonic to subsonic speeds is known as the termination shock. This boundary is not a wall, it is a transition region shaped by pressure differences and magnetic interactions. Voyager's instruments detected changes in particle energy and density that indicated it had crossed this threshold. The flow of the solar wind became more turbulent. Shock waves formed. The environment grew more complex. Crossing the termination shock was significant, but it did not mean Voyager had left the solar system. It meant the spacecraft had entered the outer layers of the Sun's domain, a region sometimes called the Helios-heath. Here, solar particles pile up, compressed and heated as they push against the interstellar medium. In this region, particle densities increased. Magnetic fields shifted orientation. Voyager's detectors recorded variations that did not fit neatly into earlier models. The heliosphere, it turned out, was not a smooth, symmetrical bubble. It was irregular, influenced by the direction of the interstellar magnetic field and by variations in solar output over time. One of the challenges in studying this boundary was instrumentation. Voyager was never designed specifically to probe the heliosphere's edge. Some instruments had failed years earlier. Others were operating at the limits of their sensitivity. Interpreting the data required care and creativity. Scientists had to rely on indirect measurements, changes in particle counts, shifts in magnetic field direction, variations in plasma waves. Each clue by itself was ambiguous. Together they began to form a picture. The heliosphere's outer boundary, called the heliopause, marks the point where the pressure of the solar wind balances that of interstellar space. Beyond this boundary, the Sun's influence wanes, and the local environment is dominated by particles and fields from the galaxy at large. Determining when Voyager crossed this boundary was not straightforward. Unlike a planetary flyby, there was no single moment that could be marked with certainty. Instead, scientists debated the interpretation of the data. Some indicators suggested the crossing had occurred. Others lagged behind. Eventually, a consensus emerged. Voyager had entered a region where the density of interstellar particles increased sharply, while solar particles dropped away. Magnetic field measurements showed a change in orientation consistent with leaving the heliosphere. Plasma wave data confirmed higher densities typical of interstellar space. This moment redefined what it means to leave home. The solar system, it became clear, is not just a collection of planets orbiting the Sun. It is an extended environment shaped by solar activity, stretching far beyond the last planet. Leaving it requires passing through layers, each governed by different physical processes. Voyager's measurements challenge simple definitions. Is the solar system defined by gravity, by planets, by the reach of the solar wind, or by something else entirely? The answer depends on context. Voyager revealed that boundaries in space are rarely sharp. They are regions of transition shaped by competing forces. There was also a practical lesson. Even at these extreme distances, the Sun still mattered. Solar cycles influence conditions far beyond the planets. Changes in solar activity propagated outward over years, altering the structure of the heliosphere and the timing of boundary crossings. This added a temporal dimension to the journey. Voyager was not just moving through space, it was moving through the delayed effects of past solar behavior. The Sun it was leaving behind was not the Sun of today, but the Sun of years earlier. The act of leaving the solar system then became less about a finish line and more about a change in conversation. The spacecraft's instruments shifted focus from solar particles to interstellar ones. The dominant magnetic field was no longer the Sun's. The environment grew quieter in some ways and more uniform in others, yet even here uncertainty remained. Instrument limitations meant that some properties could only be inferred. Models had to be refined. Assumptions were tested against sparse data. Voyager was doing science at the edge of detectability. This uncertainty did not diminish the achievement, it defined it. The boundary region between solar and interstellar space is one of the most difficult environments to study, precisely because it is transitional. Voyager did not provide a final answer. It provided the first direct evidence. Leaving the solar system did not mean leaving influence entirely. Gravity still bound Voyager loosely to the Sun. The spacecraft remained a member of the solar system in a dynamical sense, even as it entered interstellar space in a physical one. These overlapping definitions coexisted without contradiction. What Voyager demonstrated was that home is not a place with clear borders, it is a gradient, a fading of familiar forces rather than an abrupt departure. The Sun's presence diminishes slowly, replaced by the background of the galaxy. As Voyager continued onward, the heliosphere receded behind it, not as a line crossed, but as a region left behind piece by piece. The spacecraft did not announce its departure, it simply recorded the change. In doing so, it redefined the edge of the solar system from a concept into a measurable phenomenon. Not a boundary drawn on a map, but a set of physical conditions that can be observed, quantified, and debated. Leaving home, it turned out, was not about distance. It was about influence. And Voyager had reached the point where the Sun was no longer in charge. Interstellar space is often imagined as a dramatic emptiness, a sharp contrast to everything that comes before it. Voyager revealed something quieter and more subtle. Entering interstellar space was not a leap into nothing, but a transition into a different kind of something, governed by different forces and carrying a different history. Beyond the heliosphere, the dominant influence is no longer the Sun. The charged particles flowing outward from it thin dramatically, replaced by particles that originate elsewhere in the galaxy. This change was first hinted at through measurements of plasma density. Voyager's instruments detected a sudden increase in the number of charged particles surrounding the spacecraft. The density was low by everyday standards, but it was significantly higher than what had been measured in the outer reaches of the heliosphere. Plasma in this context refers to a gas so thin and energetic that atoms are stripped of electrons. It fills much of the space between stars. Voyager's data showed that this interstellar plasma is not uniform but structured, shaped by magnetic fields and long-term galactic processes. The increase in density was one of the strongest indicators that the spacecraft had crossed into a new environment. Magnetic field measurements reinforced this conclusion. Inside the heliosphere, the magnetic field is carried outward by the solar wind and arranged into a spiral pattern due to the Sun's rotation. Beyond it, the magnetic field belongs to the galaxy itself. Voyager detected a change in field strength and stability, consistent with entering a region dominated by the Milky Way's magnetic influence rather than the Sun's. Interestingly, the direction of the magnetic field did not change as dramatically as some models had predicted. This sparked debate and refinement of existing theories. The heliosphere, it seemed, aligns more closely with the surrounding galactic field than expected. Voyager's observations forced scientists to reconsider how the Sun's bubble interacts with its galactic environment. Radiation conditions also shifted. Inside the heliosphere, solar particles dominate. Outside, high-energy cosmic rays become more prevalent. Voyager measured an increase in these galactic cosmic rays, particles accelerated by distant astrophysical events such as supernovae. At the same time, the flux of solar particles dropped sharply. This change mattered not only scientifically but practically. Cosmic rays carry far more energy than typical solar particles. They pose a greater threat to electronics and, hypothetically, to biological tissue. Voyager's continued operation in this environment provided real-world data on how spacecraft systems endure prolonged exposure to galactic radiation. Together, these measurements built a case. No single instrument could declare the spacecraft interstellar. Some instruments were no longer functioning. Others operated at the edge of their sensitivity. Confirmation required consistency across multiple lines of evidence. Plasma wave instruments detected oscillations characteristic of higher density interstellar plasma. Particle detectors recorded changes in composition and energy. Magnetometers measured a steadier, stronger field. Each dataset reinforced the others. The picture that emerged was coherent. This is where the scientific meaning of the word interstellar becomes important. It does not simply mean far away. It describes a region where the local environment is shaped by the galaxy rather than by a single star. Interstellar space is defined by origin of particles, by dominant magnetic fields, and by long-term equilibrium rather than by proximity to planets. Voyager did not cross into a void, it crossed into the background of the Milky Way. That background is not static. It carries the imprint of ancient events, shock waves from long vanished stars, magnetic structures stretched over light years, matter cycled through generations of stellar birth and death. Voyager's instruments sampled this environment directly for the first time. The spacecraft's limitations made this achievement more impressive. It was never designed for this role. Some key plasma instruments had failed decades earlier. Others were operating in modes their designers had not originally intended. Scientists had to adapt, using indirect measurements and creative interpretation. This adaptability echoed earlier phases of the mission. Voyager had always been asked to do more than expected. Interstellar space was simply the latest request. There was also a shift in perspective. Inside the solar system, measurements are often anchored to known objects. Planets provide reference points. Distances are contextual. In interstellar space, there are no nearby landmarks. Everything is relative. Voyager's data became less about position and more about properties. The environment it entered was quieter in some respects. Fewer fluctuations driven by solar storms, more uniform particle populations. Yet it was also harsher, bathed in radiation that had travelled for millions of years before arriving. This contrast underscored an important idea. Interstellar space is not empty because nothing happens there. It is empty because everything happens slowly. Processes unfold over immense distances and timescales. Voyager's measurements captured only a thin slice of that vastness, but even that slice reshaped understanding. Confirmation of interstellar entry was not announced lightly. Scientists debated interpretations for years. Papers were written, revised, challenged. The criteria for declaring the crossing were scrutinized carefully. In the end, consensus emerged not from a single dramatic signal, but from the convergence of many subtle ones. This cautious approach reflected the nature of the boundary itself. Interstellar space does not begin with a line. It emerges gradually as one influence fades and another takes over. Voyager documented that fading with precision born of patience. The moment carried symbolic weight, but it was grounded in measurement. A spacecraft built to study planets had become an interstellar probe, not by design, but by endurance. Entering interstellar space did not end the mission, it redefined it. The questions changed. Instead of asking how planets work, scientists began asking how the galaxy fills the space between them, how matter behaves when freed from stellar dominance, how magnetic fields shape vast, diffuse regions. Voyager's presence in interstellar space remains modest. It samples a tiny volume. Yet that volume was previously untouched. In science, First contact with a new regime matters, no matter how small the sample. The spacecraft continues to move through this environment, gathering data point by point. Each measurement is local, specific, and unremarkable on its own. Together they form the first direct record of what it means to be between stars. Interstellar space, once a concept defined by absence, became a place defined by properties. Voyager made that possible simply by continuing to go where nothing had been measured before, and in doing so it transformed the unknown into something quietly knowable. Communication with Voyager works not because space is empty, but because it is predictable. Between Earth and the spacecraft lies an enormous distance filled with almost nothing to interfere. That emptiness is what makes the conversation possible, even as it grows increasingly fragile. The challenge begins with signal strength. Voyager transmits using a radio signal that spreads outward in all directions as it travels. This spreading follows a simple physical rule. As distance increases, the signal's energy is distributed across a larger area. The amount of energy arriving at any given point drops rapidly with distance. In practical terms, every doubling of distance reduces the signal's strength to a quarter of what it was before. This relationship is described by the inverse square law, which can be written in words as signal strength decreases in proportion to 1 divided by the square of the distance. By the time Voyager's signal reaches Earth, it is extraordinarily weak. The power arriving at a receiving antenna is less than that produced by a wristwatch battery, spread thin across a sphere billions of kilometers wide. Pulling meaningful information out of that faint whisper requires infrastructure built specifically for listening. That infrastructure is the Deep Space Network. Operated by NASA, it consists of large radio antennas positioned around the world, spaced so that as Earth rotates, at least one is always able to point toward Voyager. These facilities are located in widely separated regions to reduce interference and ensure continuous coverage. The antennas themselves are enormous. Their size matters because a larger dish can collect more of the incoming signal. Even so, size alone is not enough. Receivers must be exceptionally sensitive, capable of distinguishing Voyager's transmission from background noise generated by cosmic sources, Earth's atmosphere, and even the electronics within the receiver itself. Communication is not simply a matter of pointing an antenna and listening. Signals must be carefully timed, encoded, and decoded. Voyager transmits data using a precisely defined format, one that allows errors to be detected and corrected. This is essential because noise inevitably corrupts some portion of the signal during its long journey. Error correction works by adding redundancy. Data bits are arranged so that inconsistencies can be identified and, within limits, repaired. This process reduces the effective data rate, but increases reliability. As Voyager moved farther away, engineers adjusted transmission strategies, favoring accuracy over speed. The data rate itself has dropped dramatically over time. Early in the mission, Voyager could send information relatively quickly. Today, transmission rates are measured in bits per second. Entire images can take hours to arrive. Scientific readings are prioritized carefully. There is no room for waste. Timing adds another layer of complexity. Radio waves travel at the speed of light, which is fast but not instantaneous. One-way communication delays are now measured in many hours. When a command is sent from Earth, it reaches Voyager long after the decision to send it was made. Any response arrives hours after that. This delay changes the nature of control. There is no real-time interaction. Engineers cannot ask a question and wait for an immediate answer. Instead, they plan sequences of commands days in advance, anticipating how Voyager will respond and what conditions it will be in when the instructions arrive. This requires trust in both the spacecraft and the physics governing its motion. Voyager's systems must execute commands exactly as intended, without confirmation until much later. Earth-based teams must accept uncertainty as a normal operating condition. Listening is equally demanding. Receiving stations schedule time to track Voyager, coordinating observations across continents. The signal must be locked onto precisely. Even tiny pointing errors can cause the antenna to miss the signal entirely. Extracting data from the signal is a careful process. The received radio waves are converted into electrical signals, amplified, filtered, and processed. Noise is reduced statistically, often by integrating the signal over long periods. This means listening patiently, letting the signal accumulate until it rises above the noise floor. There are practical limits to this process. At some point, the signal will become too weak to recover reliably. This is not a sudden cut-off, but a gradual loss of clarity. Data rates drop. Error rates increase. More time is required to extract less information. Power on Voyager also limits communication. As its energy supply declines, the transmitter must operate at lower power. Engineers adjust antenna usage and transmission schedules to compensate, but physics imposes a hard boundary. You cannot transmit what you cannot power. Despite these challenges, communication has continued far longer than expected. This is partly due to conservative design, and partly due to improvements on Earth. Receivers have become more sensitive. Data processing techniques have advanced. What was once undetectable has become recoverable. This asymmetry is important. Voyager's technology is frozen in time. Earth's is not. The ability to keep listening has improved even as the spacecraft's ability to speak has diminished. The conversation persists because the listener has learned to listen better. There is also coordination involved. The Deep Space Network supports many missions simultaneously. Time on its antennas is carefully scheduled. Voyager competes with newer spacecraft exploring Mars, asteroids, and the outer solar system. Priorities are balanced constantly, yet Voyager continues to earn its place. Its data is unique. No other spacecraft occupies the same region of space. No other instrument can replace its measurements. As long as it can transmit anything at all, it remains scientifically valuable. Communication across such distances highlights a broader truth about space exploration. Distance does not simply separate objects, it reshapes relationships. Control becomes indirect. Feedback becomes delayed. Responsibility shifts from reaction to planning. There's also something quietly humbling about the process. A signal generated by a machine built decades ago travels through billions of kilometers of space and is caught by a structure on Earth, decoded by software, and turned back into knowledge. The entire chain must work. Failure at any point breaks the connection. That fragility makes each successful transmission meaningful, even if the data itself is routine. A temperature reading, a particle count, a magnetic field measurement. Each one confirms that the line is still open. Eventually that line will close, not because Voyager stops moving, but because communication becomes impossible. The spacecraft will continue onward in silence, indistinguishable from countless other objects drifting through the galaxy. Until then, contact is maintained across nothing. Not through force or proximity, but through patience, precision, and a deep understanding of how signals behave in space. In that ongoing exchange, Earth and Voyager remain linked, not by distance, but by the physics that allows information to cross it. From the beginning, Voyager's mission carried a quiet certainty. Power would run out. Not suddenly, not dramatically, but steadily and predictably. There was no scenario in which the spacecraft could continue indefinitely. Its endurance was impressive, but it was never infinite. The source of Voyager's power is radioactive decay, a process as reliable as it is unforgiving. Inside its radioisotope thermoelectric generators, atoms of plutonium slowly break apart, releasing heat. That heat is converted into electricity. The physics is simple and beautifully indifferent. Each year, a fixed fraction of the fuel decays. No intervention can speed it up or slow it down. This decline follows a curve that engineers could calculate decades in advance. The power output decreases smoothly over time. Following what can be described in words as available power decreases exponentially as radioactive fuel decays. There are no surprises in the math, only consequences. Early in the mission, power margins were generous. Instruments could operate simultaneously. Heaters kept components comfortably within temperature limits. Communication systems ran without concern for efficiency. Voyager lived in abundance. That phase ended quietly. As the years passed, the available electrical power shrank. At first, the loss was barely noticeable. Then it became something that required planning. Engineers began to make choices, not about what to add, but about what to turn off. Every instrument consumes power, some more than others. Some provide data that overlaps with other sensors. Some measure conditions that are no longer changing rapidly. The challenge was to decide which instruments remained essential and which could be sacrificed without crippling the mission's core goals. This process was methodical and deliberate. Instruments were evaluated based on scientific value, power consumption, and likelihood of continued usefulness. When one was shut down, it was usually done permanently. Restarting later would require power that no longer existed. There was also heat to consider. Voyager does not only use electricity to operate instruments, it uses it to stay warm. In the cold of deep space, components lose heat constantly. Without sufficient power, temperatures can drop below safe operating limits. This created a delicate balance. Turning off an instrument saved electrical power, but it could also reduce heat generation in that part of the spacecraft. Engineers had to consider thermal consequences alongside electrical ones. A decision that looked sensible on paper could create unexpected cold spots elsewhere. To manage this, Voyager relied increasingly on passive thermal strategies. Heat generated by remaining systems was shared carefully. Insulation became more important than ever. Heaters were used sparingly, activated only when absolutely necessary. The spacecraft's gradual cooling mirrored its narrowing scientific focus. Early in the mission, Voyager could afford to be broad. It measured many things at once. As power declined, it became selective. The mission shifted from comprehensive observation to targeted measurement. This narrowing was not a failure, it was adaptation. Decision-making under these conditions carried a particular weight. Every choice was irreversible. Turning off an instrument meant accepting that whatever it could have measured in the future would remain unknown. Engineers and scientists debated these decisions carefully, aware that they were shaping the final chapters of the mission. There was no room for sentimentality. An instrument might have a long history of success, but history alone did not justify continued power consumption. Value was measured in future return, not past contribution. These choices were also informed by the spacecraft's environment. As Voyager moved deeper into interstellar space, some instruments became more relevant than others. Measuring solar particles mattered less. Measuring galactic particles mattered more. The mission evolved alongside its surroundings. This evolution required constant reassessment. Power projections were updated, thermal models were refined, contingency plans were developed for scenarios in which power dropped faster than expected. Despite the steady decline, Voyager continued to surprise. Systems lasted longer than predicted. Components tolerated colder temperatures than originally specified. Margins proved more forgiving than anticipated. This resilience was not accidental. It was the result of conservative design choices made decades earlier. Engineers had overbuilt where they could. They had avoided unnecessary complexity. They had assumed that the spacecraft would need to endure more than originally planned. As a result, Voyager did not approach power loss with a sudden cliff, but with a gentle slope. Scientific output diminished gradually rather than abruptly. The mission did not end one day, it faded. The shrinking power budget also affected communication. Transmitters required energy to operate. Lower power meant weaker signals. Data rates dropped further. Engineers adjusted encoding schemes and transmission schedules to compensate, squeezing as much information as possible from dwindling resources. This created a sense of urgency without panic. There was no single deadline. Instead, there was a moving horizon. Each year brought slightly fewer options. Each successful transmission became more precious. There is a temptation to frame this stage of the mission as decline alone. In reality, it was refinement. Voyager became increasingly focused on what only it could do. Its measurements of interstellar space grew more valuable as its planetary instruments fell silent. Power loss also underscored a broader truth about exploration. Longevity is not about resisting decay. It is about planning for it. Voyager's designers never imagined stopping decay. They planned around it. The spacecraft's continued operation is not a story of defying physics. It is a story of cooperating with it, accepting limits, making choices early that leave room for flexibility later. Eventually, power will drop below the threshold required to keep the transmitter running. Instruments will go quiet. Temperatures will fall beyond tolerance. Voyager will become a silent object, still moving, still intact, but no longer communicating. That moment is not yet here, but it is no longer abstract. It is part of operational planning. Engineers do not ask if it will happen. They ask how best to use the time that remains. The gradual narrowing of scientific output has a paradoxical effect. As the mission simplifies, its meaning sharpens. Each remaining data stream represents something that cannot be measured anywhere else. Power running out does not erase what Voyager has done. It completes it. It defines the mission's shape, giving it an ending that reflects its beginning. A carefully managed process, guided by physics, carried out with patience. Voyager's story was never about lasting forever. It was about lasting long enough to matter. By the time Voyager reached interstellar space, it had quietly overturned one of the most persistent ideas about the universe. Space is not empty. It is structured, layered, and active, even in regions where nothing obvious seems to happen. Before Voyager, much of what was known about space came from theory and remote observation. Telescopes could infer properties from light and radiation, but direct measurement was limited to regions close to Earth. Beyond the planet, space was often treated as a backdrop rather than a subject in its own right. Voyager changed that by turning space itself into the object of study. One of the clearest lessons was that space is shaped by gradients. Matter, energy, and influence do not stop abruptly. They thin, fade, and overlap. The sun's presence does not end at the last planet. It extends outward through the solar wind. Carried by charged particles and magnetic fields, that shape a vast region far larger than the planetary system itself. Voyager revealed that this solar influence weakens gradually. Particle densities decline. Magnetic fields shift orientation. Energetic processes driven by the Sun give way to those driven by the galaxy. The transition is not a line, it is a region, and that region has structure. This challenged simple definitions. Where does the solar system end? Is it defined by gravity, by planets, by the reach of the solar wind, or by something else? Voyager showed that all of these definitions are valid in different contexts. Space does not offer a single answer. It offers layers of influence stacked on top of one another. The idea of continuity emerged strongly from the data. Solar space and interstellar space are not separate realms stitched together awkwardly. They are connected environments governed by the same physical laws. The difference lies in scale and dominance. Near the Sun, solar processes overwhelm galactic ones. Far away, the balance reverses. Voyager measured this handover directly. The spacecraft recorded how solar particles dwindled while galactic cosmic rays became more prominent. It detected changes in magnetic fields that reflected a shift in authority from the Sun to the Milky Way. These observations showed that space is not divided into compartments, but organized into gradients shaped by competing forces. Another lesson was that space is dynamic even where it appears calm. Interstellar plasma may seem static compared to planetary atmospheres, but it carries the imprint of ancient events. Shock waves from long vanished stars ripple through it. Magnetic fields stretched across light years guide particle motion. Voyager's instruments sampled a medium shaped by processes operating on timescales far beyond human experience. This introduced a new sense of time into space science. Planetary weather unfolds over hours and days. Interstellar processes unfold over thousands or millions of years. Voyager's measurements offered a glimpse into that slower rhythm, reminding scientists that stillness often reflects scale rather than inactivity. Voyager also taught humility about observation. At extreme distances, measurement becomes difficult. Instruments reach the limits of their sensitivity. Data arrives slowly and sparsely. Scientists must interpret subtle signals without the comfort of redundancy or immediate confirmation. This limitation is not a weakness of the mission. It is an inherent property of distance. The farther one goes, the harder it becomes to know precisely what is being measured. Voyager made this challenge explicit. It showed that exploration is not just about reaching new places, but about understanding what can and cannot be known there. Some quantities could be measured directly: particle counts, magnetic field strength, plasma density. Others had to be inferred: boundary locations, environmental transitions, long-term trends. Voyager's success depended on combining many imperfect measurements into a coherent picture. This process reshaped scientific practice. Models were refined to accommodate sparse data. Assumptions were tested against single data points stretched over long intervals. Uncertainty became part of the narrative rather than something to be eliminated. Voyager's journey also reframed scale. Distances that once seemed immense became part of a continuum. The solar system, once thought of as vast, appeared as a small structure embedded within a much larger galactic environment. The Sun's influence, impressive on planetary scales, became just one bubble among many in the Milky Way. This perspective shift was not abstract. It was grounded in measurement. Voyager showed exactly how far the Sun's reach extended and how it compared to the surrounding medium. The numbers made the scale tangible. There was also a lesson about patience. Voyager did not deliver its insights quickly. Its most transformative contributions came decades after launch, long after its planetary encounters had ended. The mission demonstrated that some questions require not faster instruments, but longer commitment. In a scientific culture often driven by short timelines and immediate results, Voyager stood apart. It rewarded endurance. It showed that understanding space sometimes means waiting for the environment to change around you, rather than seeking constant novelty. Voyager reshaped cosmic perspective in another way as well. It blurred the distinction between destination and journey. The spacecraft did not set out to study interstellar space, yet by continuing onward it became the first to do so directly. Discovery emerged not from a new objective, but from persistence. This has implications beyond this mission. It suggests that exploration benefits from flexibility, that missions designed with narrow goals may still uncover unexpected insights if they are allowed to continue operating. Voyager's greatest discoveries were not all planned, they were earned through longevity. The mission also highlighted the role of scale in shaping intuition. On Earth, space feels empty because it is vast compared to human dimensions. Voyager showed that even at the largest scales accessible to direct measurement, space has texture. It has density gradients, magnetic structure, and energetic variation. This does not make space crowded, it makes it interesting. Perhaps the most profound lesson is that space is not defined by absence, but by relationship. Particles interact with fields. Fields interact with flows. Local conditions reflect distant causes. Voyager measured these relationships directly, turning abstract concepts into physical data. In doing so, it changed how space is taught, modelled, and imagined. The solar system became part of a larger ecosystem rather than an isolated neighbourhood. Interstellar space became a measurable environment rather than a theoretical void. Voyager also clarified the limits of exploration. No matter how far a spacecraft travels, it samples only a tiny volume. Its measurements are local. Extrapolation requires caution. Voyager did not map the galaxy. It touched it. That touch, however, was enough to confirm that the galaxy is accessible to measurement in principle, that its properties can be studied directly, not just inferred from afar. Voyager opened that door. The spacecraft's impact on cosmic perspective lies not in dramatic imagery, but in quiet redefinition. Space became something with layers rather than emptiness. Boundaries became regions rather than lines. Distance became a variable rather than a barrier. What Voyager taught us about space is not a single fact, but a way of thinking. That the universe reveals itself gradually. That structure persists even where matter is sparse. That understanding emerges from continuity rather than spectacle. Voyager did not make space smaller, it made it more coherent, and in doing so it reminded us that exploration is not only about where we go, but about how patiently we are willing to observe what surrounds us along the way. Voyager's journey makes time visible in a way few human projects ever have, not as something measured by clocks on a wall, but as something embedded in motion, distance, and delay. The spacecraft does not just travel through space, it travels through timescales that stretch far beyond ordinary experience. The mission began within a single human generation. Many of the engineers who worked on Voyager were young adults when it launched. Some lived long enough to see it leave the solar system, others did not. The spacecraft outlasted careers, institutions, and assumptions about how long a mission could reasonably be expected to operate. In human terms, Voyager's lifetime already feels extraordinary. Decades of continuous operation would be remarkable for almost any machine. Yet when placed against interstellar scales, those decades barely register. Voyager has been travelling for a long time by human standards. By cosmic standards, it has only just begun. This contrast reshapes how duration is understood. Interstellar distances are vast not just in space, but in time. Even moving at tens of thousands of kilometers per hour, Voyager advances only a tiny fraction of a light year over many decades. The nearest star systems lie so far away that reaching them would require timescales comparable to the rise and fall of civilizations. To travel the distance to even the closest star at Voyager's speed would take many tens of thousands of years. That span exceeds recorded human history. It stretches beyond agriculture, writing, and cities. It reaches back into a time when humans lived as small, scattered populations. Placed in that context, Voyager is not racing toward a destination. It is drifting across a scale where motion itself becomes a long-term condition, rather than a journey with an end point. Time also enters the mission in a subtler way. Every signal Voyager sends arrives from the past. The data received on Earth describes conditions that existed hours earlier, sometimes longer. There is no way to observe Voyager's present state directly. It can only be reconstructed after the fact. As distance increases, this delay grows. Commands are sent based on predictions of where Voyager will be, not where it is. The spacecraft responds to instructions long after they're issued. The entire relationship operates across a widening temporal gap. This turns communication into a form of archaeology. Engineers interpret telemetry that describes a past moment, compare it to models, and decide what to do next without immediate feedback. The mission unfolds out of sync with itself. On an interstellar scale, this delay is modest. Light from distant stars takes years, decades, or centuries to reach Earth. Voyager's signals are still relatively close, yet the principle is the same. Information travels at a finite speed. Time cannot be bypassed. Voyager also demonstrates the longevity of human-made objects in space. On Earth, structures decay quickly. Weather, water, and biology erode materials relentlessly. In interstellar space, those forces are absent. Once power fades and systems fall silent, Voyager will not disintegrate, it will persist. The spacecraft will continue moving long after it stops communicating. Its structure will remain largely unchanged for immense periods. Barring collisions, it may outlast the surface of Earth as it exists today. Continents will shift, climates will change, Voyager will still be travelling. This endurance is not intentional in a dramatic sense. Voyager was not designed to be eternal. It is durable because space is gentle in its own way. The absence of atmosphere and liquid water preserves objects rather than destroying them. This creates a strange inversion. On Earth, time destroys. In interstellar space, time preserves. The golden record attached to Voyager embodies this idea. Its creators knew that the object would likely survive far longer than the people who made it. The record was built to persist across geological and perhaps astronomical timescales, not because that outcome was guaranteed, but because it was possible. Time in this context becomes a medium rather than an enemy. Voyager's instruments also revealed how time operates as a physical constraint. Radioactive decay governs power loss. That decay follows a schedule set by nuclear physics, not by human desire. No amount of ingenuity can change it. The mission's lifespan is shaped by half-lives measured in decades. Similarly, the environment Voyager now travels through reflects processes unfolding over millions of years. Interstellar plasma carries the imprint of ancient supernovae, Magnetic fields are shaped by galactic rotation over immense spans of time. Voyager samples conditions created long before humans existed. This layering of timescales creates a kind of compression. Data gathered in a moment reflects events separated by vast durations. A particle detected today may have been accelerated by a star that exploded long ago. Voyager acts as a bridge between those times, connecting immediate measurement to ancient cause. There is also a psychological dimension. Humans are accustomed to projects that conclude within a lifetime. Voyager challenges that expectation. Its story extends beyond individual experience. It belongs to institutions, to records, and eventually to history rather than memory. This shift matters. It changes how success is defined. Voyager's value is not measured only by immediate return, but by cumulative contribution over decades. It rewards patience rather than urgency. Interstellar time also reframes ambition. The distances involved make clear that human technology, impressive as it is, operates on modest scales compared to stellar evolution. Stars live for billions of years. Galaxies evolve over even longer spans. Voyager's journey is a brief note within those narratives. Yet that brief note matters because it is deliberate. Voyager's movement is intentional, guided and measured. It is a conscious act within an otherwise indifferent universe. Time emerges here not as an abstraction, but as a limiting factor that shapes every decision. Power fades, signals delay, motion accumulates slowly. Nothing can be rushed. The mission unfolds at the pace allowed by physics. Voyager teaches that time cannot be conquered, only accommodated. Success comes from aligning expectations with reality rather than trying to compress it. As the spacecraft continues outward, it enters regimes where change is slow and subtle. Years pass with little visible difference, yet distance continues to accumulate. The journey proceeds whether or not anyone is watching. In this way, Voyager embodies a different relationship with time, not one of deadlines and urgency, but one of continuation. The spacecraft moves because it was set in motion, and it will keep moving until something stops it. This reframing has consequences for how the universe is imagined. Space is not just large, it is old. Processes unfold slowly. Understanding emerges gradually. Voyager fits into that rhythm rather than fighting it. Perhaps the most important lesson is that time is not merely a background against which events occur. It is an active constraint that shapes what can be known, when it can be known, and how long that knowledge remains relevant. Voyager's journey is long, not because it is slow, but because the universe is vast. Its duration is not excessive. It is appropriate to the scale it inhabits. In that sense, Voyager has not been travelling for a long time at all. It has been travelling for exactly as long as interstellar space requires. Voyager's future does not arrive at a destination. It unfolds as continuation. Once the last instrument falls silent and the final signal fades into background noise, the spacecraft does not complete its mission in any conventional sense. It simply changes state. From that point onward, Voyager becomes an object rather than an operation. Its trajectory through the Milky Way is predictable in principle, even if uncertain in detail. The spacecraft is moving relative to the Sun, and the Sun itself is moving relative to the galaxy. Together, these motions trace a slow arc through the local spiral arm. Voyager is not headed toward any particular star. It is drifting through a region shaped by galactic rotation and local stellar motion. Over tens of thousands of years, Voyager will pass through different interstellar environments. Some regions will be slightly denser, others more rarefied. Magnetic fields will vary subtly. None of these changes will register dramatically on the spacecraft. It has no active systems left to respond. It will simply experience them passively. The probability of Voyager encountering anything substantial is extremely low. Interstellar space is vast and sparse. Even over millions of years, the chance of collision with a star, planet, or large object is effectively negligible. Dust grains and atomic particles may strike it occasionally, but these impacts are unlikely to cause significant damage. Space is not dangerous because it is violent. It is safe because it is empty. This emptiness is what allows Voyager to persist. With no atmosphere to corrode it, no liquid to erode it, and no biological processes to dismantle it, the spacecraft's structure may remain intact for extraordinary lengths of time. Its surfaces will accumulate radiation damage slowly. Materials will age quietly. But disintegration is not inevitable on human or even geological timescales. Voyager's long-term survival depends less on durability than on chance. A rare high-energy particle could eventually disrupt a component. A collision with a fast-moving grain could alter its orientation. Yet even these events would not destroy the spacecraft outright. They would simply change it, incrementally. Eventually communication will end, not because Voyager stops moving, but because it stops speaking. Power loss will shut down the transmitter. Antennas on Earth will no longer detect a signal. The final data point will arrive without fanfare. There will be no clear moment marking this transition. One day, the signal will fail to lock. Engineers will try again. They will listen longer. They will integrate over time. Eventually, the conclusion will be unavoidable. Voyager will have gone quiet. That silence is not failure. It is the expected outcome of a finite energy supply operating in an infinite environment. Once communication ends, Voyager will cease to be a mission in any operational sense. There will be no commands, no telemetry, no updates. The spacecraft will no longer participate in the scientific process as an active contributor. Yet it will not disappear. Voyager will continue as a passive artifact, moving through interstellar space with no awareness of time or place. It will carry the marks of its origin. Manufactured materials, machined surfaces, the golden record sealed to its side. These features distinguish it from natural debris, even as it becomes indistinguishable in motion. In this state, Voyager occupies a curious category. It is not a probe, it is not debris, it is not a message being sent or received. It is a record of an action that has already occurred. This open-endedness is unusual in human projects. Most artifacts are designed with lifetimes, endpoints, or disposal plans. Voyager was designed to function. What happens after function ends was not the focus. Yet that afterlife may be the longest phase of its existence. Over time, Voyager will drift relative to the stars that once framed its journey. Constellations will distort. Nearby stars will move. The sky around the spacecraft will change slowly, imperceptibly, but continuously. If Voyager passes near another stellar system in the distant future, it will do so silently. It will not announce itself. It will not react. Any interaction would be governed entirely by physics rather than intention. This lack of ending invites reflection, but it does not require interpretation. Voyager's future is not mysterious in a narrative sense. It is open because nothing remains to conclude it. The mission's meaning does not depend on what happens next. It rests on what has already occurred. The data returned, the boundaries crossed, the environments measured. These contributions are complete even if the journey continues. Voyager's open-ended future highlights a broader idea about exploration. Some journeys do not conclude with arrival. They conclude with exhaustion of the means to observe. What remains continues without documentation. This is not tragic. It is simply a mismatch between human attention and cosmic scale. The spacecraft's continued motion does not require monitoring to be real. It does not need acknowledgement. It exists because it was set in motion, and nothing has yet stopped it. In this sense, Voyager is less like a traveller and more like a fossil. Not preserved in rock, but preserved in motion. It carries information not in signals, but in structure. The golden record will remain attached, sealed, unread, and likely unplayed. Its presence does not depend on an audience. It is part of the artifact rather than a message awaiting reception. Over very long timescales, Voyager may eventually be altered beyond recognition. Radiation may erode surfaces. Collisions may reshape components. But even then, fragments will continue along similar paths, preserving motion even if form is lost. There is no planned finale, no final chapter written into the mission design. Voyager was never meant to stop in a way that could be observed. It was meant to go until it could not report back, and then continue anyway. This lack of an ending is not a flaw. It is a consequence of scale. In an environment where time stretches beyond individual experience, conclusions are artificial. Voyager's story ends for humans when contact is lost. For the spacecraft, nothing changes. It moves on, unchanged by our absence. In that continuation lies a quiet lesson. Exploration does not require closure to be meaningful. Some of the most significant journeys are those that simply keep going, not toward a goal, but away from an origin. Voyager is no longer travelling to somewhere. It is travelling from somewhere. And that distinction, once made, never needs to be resolved. Voyager's journey invites reflection, but it resists grand conclusions. It was never designed as a symbol, and treating it as one risks misunderstanding what it actually accomplished. Voyager was a measurement tool, a carefully engineered instrument sent to gather data where none had been gathered before. Its meaning emerges not from intention, but from accumulation. From the beginning, Voyager did not ask philosophical questions. It measured particle densities. It recorded magnetic fields. It counted radiation events. It returned images and numbers. Any broader interpretation came later, layered on top of results that were narrow, precise, and technical. This distinction matters. Science advances not by symbolism, but by constraint. Voyager's success came from respecting limits rather than ignoring them. Limited power, limited memory, limited ability to respond in real time. These constraints forced clarity. Every measurement had to justify its cost. Every decision had to accept trade-offs. That discipline is part of Voyager's legacy. It demonstrated how much can be learned when ambition is paired with restraint. The scale Voyager encountered demands humility. The solar system turned out to be larger and more complex than expected. Interstellar space proved structured rather than empty. Even so, the regions Voyager sampled represent a tiny fraction of what exists. The spacecraft did not conquer space. It touched it lightly. This humility extends to interpretation. Voyager showed where direct measurement is possible, and where inference must take over. Beyond a certain distance, instruments reach their limits. Signals weaken. Data becomes sparse. Models become necessary, but models always carry assumptions. Voyager did not eliminate uncertainty. It clarified where uncertainty begins. That clarification is one of science's most valuable outcomes. Knowing what cannot yet be known is as important as discovering what can. Voyager mapped not just environments, but boundaries of understanding. The mission also revealed the limits of exploration by machines. Voyager can travel where humans cannot. It can survive cold, radiation, and isolation. Yet it cannot adapt creatively. It cannot ask new questions on its own. It follows instructions written decades earlier, executing logic designed for situations long past. This is not a flaw. It is a reminder that exploration by machines and exploration by humans serve different roles. Machines extend reach. Humans extend interpretation. Voyager gathered the data. Humans give it meaning. Even so, there are places Voyager can reach that no human ever will, at least not physically. Interstellar space is accessible to machines precisely because it is inhospitable to biology. That division shapes future exploration. Machines will continue to go farther. Humans will continue to interpret what returns. Voyager also reframes the relationship between knowing and reaching. The spacecraft will never arrive at another star. It will never explore another planetary system. Yet knowledge about these systems continues to grow through telescopes and theory. Knowing does not require presence. Presence does not guarantee understanding. Voyager's contribution lies in anchoring theory to measurement. It provided ground truth. It allowed models to be tested against reality. In doing so, it strengthened the connection between abstract physics and physical space. Within the broader history of science, Voyager occupies a specific place. It was not the first spacecraft. It was not the fastest. It did not carry the most advanced technology by modern standards. What set it apart was duration. Voyager demonstrated the value of a long-term observation. Many of its most important contributions came long after its original mission was complete. The crossing of the heliosphere, the entry into interstellar space. These were not planned milestones, they were consequences of persistence. This challenges how success is measured. Short missions deliver fast results. Long missions reshape frameworks. Voyager did the latter. It altered how space is defined, how boundaries are understood, and how far measurement can extend. It also showed that scientific projects can outlive the context that created them. Voyager was launched during a specific political and cultural moment. That moment has passed. The mission continues to matter anyway. Its data remains relevant because physics does not age the way institutions do. There is a temptation to turn Voyager into a metaphor for humanity, a lone emissary, a hopeful message, a fragile presence in a vast universe. These readings are understandable, but they are optional. Voyager does not require them. What Voyager ultimately means is simpler and more durable. It means that careful measurement can extend understanding far beyond direct experience. It means that patience can be as powerful as speed. It means that limits, when acknowledged, can be worked with rather than fought. Voyager also reinforces a quiet truth about science. Progress often comes not from dramatic breakthroughs, but from sustained effort applied consistently over time. The spacecraft did not revolutionize understanding in a single moment. It contributed incrementally, data point by data point, year after year. That accumulation changed the picture. The journey also places human curiosity in proportion. Voyager reveals how small the region of space immediately accessible to measurement really is. It shows how much remains untouched. This is not discouraging, it is clarifying. Science does not advance by exhausting the unknown. It advances by expanding the boundary between known and unknown, one careful step at a time. Voyager expanded that boundary outward, not infinitely, not completely, but measurably. Its place in the history of science is secure not because it went far, but because it went far enough to matter. It crossed thresholds that could not be crossed before. It provided reference points that did not exist. When communication ends, nothing essential will be lost. The mission's contribution will already be complete. The spacecraft will continue, but its role in science will remain fixed in the data it returned and the questions it sharpened. There is no final revelation waiting at the end of the journey, no ultimate message, no hidden conclusion. What Voyager ultimately means is that exploration does not need resolution to be valuable. Measurement does not need narrative. Knowledge does not need an end point. The universe does not offer closure, it offers continuity. Voyager accepted that quietly and kept going. Voyager continues to move, not because it intends to, but because it was set in motion and nothing has stopped it. There is no destination ahead that matters more than the motion itself. There is only continuation, governed by the same physical laws that applied at launch and still apply now. Throughout its journey, Voyager has remained what it was built to be. A scientific instrument. It does not interpret its findings. It does not reflect on them. It measures, records, and transmits for as long as it is able. Any meaning drawn from that process belongs to those who listen, not to the machine. That distinction is important. Voyager's value does not come from symbolism or narrative. It comes from contact, direct measurement of places that could previously only be imagined. The clouds of Jupiter, the rings of Saturn, the sideways rotation of Uranus, the active winds of Neptune. These were not abstractions once Voyager passed by. They became data. Beyond the planets, the spacecraft continued to measure environments that had never been sampled directly. The solar wind thinning with distance, the slowing and reshaping of charged particles, the boundary where the sun's influence gives way to the broader conditions of the galaxy. These transitions were not inferred from theory alone. They were recorded, one reading at a time. From those measurements, understanding followed, not instantly, and not completely, but steadily. Models of planetary atmospheres were refined. Ideas about magnetic fields were tested. The structure of the heliosphere became clearer. Interstellar space shifted from a conceptual void to a measurable medium. None of this required intention on Voyager's part. The spacecraft did not need to know where it was going to make its contributions meaningful. It only needed to function long enough to observe. As power declines, that ability is narrowing. Instruments have fallen silent. Data rates have slowed. Signals grow weaker each year. This is not a malfunction or a breakdown. It is the expected result of radioactive decay and increasing distance. Physics does not negotiate. It proceeds. The fading of communication is part of the same process that carried Voyager outward in the first place. Momentum continues. Energy dissipates. Information becomes harder to extract. Nothing about this is abrupt. Nothing about it is tragic. It is simply how systems behave when allowed to run their course. Eventually the final signal will arrive. It will not announce itself as the last. It will look like every other transmission, just quieter. After that, Voyager will still exist. It will still move. It will simply no longer be heard. That silence does not undo what has already been learned. The mission's scientific contribution is not waiting on a final message. It is contained in the decades of data already returned and the frameworks those data reshaped. Voyager has shown that distance is not a barrier so much as a condition. As distance increases, immediacy disappears, control fades, observation becomes delayed and partial, yet understanding can still grow if expectations are adjusted to scale. Time, too, changes character. The journey has unfolded across human lifetimes, yet remains insignificant compared to stellar or galactic timescales. Voyager demonstrates how different those scales are, not through comparison, but through coexistence. A machine built in one era continues to operate in another, carrying assumptions forward into environments that did not exist in human experience before. What emerges from this is not a lesson about purpose, but about continuity. The same physical laws apply near Earth, near the Sun, and between stars. Gravity does not change its rules. Electromagnetism does not behave differently because no one is watching. Radio waves fade the same way everywhere. Voyager's journey does not point toward destiny. It points toward consistency. The spacecraft does not mark an endpoint in exploration. It marks a reference, a point beyond which measurement became possible for the first time. Others may follow different paths, with different tools and different goals. Voyager will remain where it is, part of the record rather than the present. There is calm in that. No urgency, no requirement for conclusion. The mission did not need to solve everything to be complete. It needed only to extend knowledge slightly beyond where it had been before. A quiet machine continues to move through space. It does so without awareness, without intention, and without pause. Its motion is not symbolic. It is physical, and in that steady motion, governed by laws that apply everywhere, Voyager becomes exactly what it has always been. A small, precise expression of how the universe behaves, observed carefully and left to continue on its way.